Greater New York, Northeast, and East Central. The problem set will be identical for everyone. And we have a few guest speakers, and we also have ICPC Live here, recording all the action. So that said, I want to introduce our regional contest directors. So we'll start from Northeast. We have RCD is Dr. Ivana Dezikova. Ivana, you want to say a few words of welcome and good luck?
Hello. Yes. Hello. Welcome, everybody. It is my great pleasure to welcome you all to the Northeast North America Divisional Championship. As you've heard, our division encompasses 3 regions, and our region, Northeast North America, is quite large geographically. So we are actually at 8 different sites. We are broadcasting from one of the sites, but we have 3 sites in Atlantic Canada, and you might be able to see our sites on the Zoom gallery. So hi, everybody. We have 1 site in Quebec. We have 2 sites in New England, and we have 2 sites in New York. So without further ado, it is my great pleasure to partner with our 2 other regions. Good luck to everybody. Have fun and all the best.
Thank you, Ivana. Our next RCD from East Central is Dr. Bob Kramer. Bob, do you have anything to add?
Well, good morning, everyone.
Bob, you had a little feedback. Are you?
Yeah, we have an echo.
Yeah, we have an echo.
There we go. I think we got it solved. All right. Good morning, everyone. Welcome. I'd like to welcome everyone from all 3 regions. We have 4 sites here in East Central. We've got Purdue, we have Windsor, we have Grand Valley State, and here at Youngstown State. I've got some rain and snow, but it'll be a fun contest. One thing I'll toss in, if you see them during the day today, make sure you thank the sysadmins. They've been putting in a lot of work at actually all of the sites across all 3 regions, getting the contest ready, squashing bugs, putting out fires. So if you see them, here we've got John and Brandon. Thank them. So they've put in a lot of long hours here getting ready. With that, good luck. Have fun. It's a fun contest. I miss my competing days. They were a long time ago. So with that, I'll turn it back over to Joe.
Thanks, Bob. And so here in Greater New York, we have 1 site, and we have 80+ teams attending in this 1 site right now, which is amazing. We're all crammed into this one rather warm room. So I too would like to thank all our volunteers, and please also thank your coaches everywhere for all the work they do, the countless hours they put in to make this possible, and all our host sites that donate all their time and resources to make this a success. We also want to thank our sponsors. So we have JetBrains and Jane Street. Here we go. So we'll start off with JetBrains here. That was a nice video from JetBrains, but you know what's a little bit better than a video from JetBrains? Is actually having the sponsors here. So JetBrains, the ICPC Global sponsor of programming tools. We have Andre, Margarita, Tatiana, and Wood is here. So if anyone come up, say a few words, please. Come. Speak, please.
Take the mic or? I still took it. Thanks everyone. Nice to see you all again. I hope you're all excited for the contest. I know there's a lot of you that are excitedly waiting for this. We hope that you guys will be using the right tools. Can sometimes maybe be our tools. Come to us, maybe we can convince you. And for us, one of the most important things for you all is you guys are passionate, young, doing exciting things, traveling to New York for this. Have fun. Enjoy what you're doing here today and make some memories. Thank you.
Thank you. Okay, next we have another sponsor, Jane Street, ICPC Titanium Multi-Regional Sponsor. So Jane Street has a long history of supporting programming competitions worldwide, of boosting several of the ICPC alumni, including multiple world finals, as well as esteemed employees. This partnership provides an exciting opportunity to sustain and nurture the incredible community of talented programmers worldwide. Jane Street, quantitative trading firm with offices worldwide, seeks to hire smart, humble individuals who love solving problems, building systems, and testing theories. If Jane Street, next great idea come from you, explore the possibilities in software engineering, quantitative trading, quantitative research, and more at Jane Street's internships. We have the URL up there, janestreet.com, join Jane Street open roles. And Jane Street also runs various educational programs in London, Hong Kong, New York, to help educate students on how Jane Street applies mathematical and computer science concepts to everyday work. And you know the URL for their initiatives on there, janestreet.com, join Jane Street programs and events. So thank you, Jane Street.
These competitions help to create and empower a new wave of talents and leaders in digital technology, and they help to grow a new generation of future programmers.
The competitive programming community is special to me just because I grew up with it. I started doing this when I was 12, and it basically kickstarted my whole career. I think it's important for Jane Street to be supporters of ICPC community because this community is very important for development of many young people who just started their journey with software engineering.
What makes ICPC special to me is that people from many different countries just come together to one place to compete against each other and create a community.
Many Jane Streeters have been involved in the same competitions you're here to take part in. I met some of my closest friends through these competitions, and to this day, I still enjoy solving problems with them.
I have been competing in ICPC for 10 years. It's what introduced me to the world of programming, to the world of problem solving. My experience at ICPC prepared me for my role at Jane Street, mostly in terms of being able to formulate my ideas clearly and implement them quickly.
I use a lot of programming skills I learned during my years in ICPC competitions.
I think Jane Street is kind of similar to ICPC in a sense that we solve a lot of complex and interesting problems in a very quick matter. And I think this experience led to me being successful in my career and having a lot of expertise in what I do.
This is how I've met a lot of friends in high school and in university. We participated in competitions. We share a passion for competitive programming, and now we work together at Jane Street.
You're surrounded by people who care about the same things as you. If I could give advice to someone competing today, I would say make as many connections as you can.
the most important part is to find your friends, gain knowledge, and have fun.
Well, thank you, Dean Street. We also want to thank the National Security Agency, NSA, as they continue to be a great supporter of ICPC North America. And we really do appreciate all they do, have done to make these contests possible. So thank you, NSA. Of course, we have to thank our judges. Chief judges are John Bonamo, John Buck, and Finn Ledbetter. And along with Zach, Liam, Bob, Isaac, Sean, Fred, Bob, and Arne. So they're the ones that put the problem set together today. So I guess you can hold your applause afterwards if you like that or not. We'll give them a little. We also have a couple of distinguished guests from ICPC visiting. ICPC Deputy Director, give you a promotion almost. Deputy Director of North American Contests and the Regional Contest Director for Pacific Northwest, Tom Paul, and the ICPC Technical Director, Dr. John Clevenger.
Thanks so much for the kind introductions, Jill. Yeah, I'm Tom. I am Deputy Director for ICPC North America. And on behalf of ICPC North America, wish you all the very best. And I want to thank Joe and Christian for allowing me to come over here. My contest is next Saturday. I'm the Director of Pacific Northwest, as it says right there. So I'm gathering all the information I can from Joe and Christian to make mine a little bit better. And I do want to say I'm really jealous because JetBrains is here with you guys. I'm working on getting them over the Pacific Northwest next year. So good luck today. Have a great time. Thanks.
And I'm John Clevenger. I'm the ICPC Technical Director responsible for technical operations all the way up to the World Finals. And I want to welcome you all here. I'm looking forward to a great contest. I also happen to be a former Pacific Northwest Regional Contest Director. Tom was the one that I suckered into taking over from me. So we're looking forward to having a great contest. And the last thing I need to tell you is something that I always tell people at the World Finals. When you go back in and sit down and are ready to start, once the schedule says we're going to start, when you get ready to start, do not touch anything at your workstation until you are told the contest starts. Okay, all right, thank you all. Congratulations, welcome, and good luck in today's contest.
Thank you, Tom. Thank you, John. Now, for our keynote speech, I would like to welcome the man who invented and developed the language many of you are using here today to solve many of these complex problems. Along with many a myriad of countless other accomplishments. So he's currently a professor of computer science here at Columbia University. So I want to welcome Dr. John Brownstrath.
Oh, it's not.
Yeah.
Great. Okay. Welcome. So, I can't tell you anything really about how to run the competition. Can't teach you anything in half an hour that would help you, would probably distract you. Anyway, I do know a little bit about the context. I have been to the World Championship, I've helped train a team, and I visited the winners of the World Contest in their home cities. But that's not what I'm going to talk about. I'm going to talk a little bit about background of computing and C++. So basically, any good language, any good solution to something starts with a problem. And if you're lucky, you get a problem that other people have too, so that your solution actually helps a lot of people. And in my case, I wanted to build a distributed Unix in 79. And if I'd been able to do so, we would have had Unix clusters 10 years early. But obviously, I couldn't do it because just one guy and didn't have a good team and didn't understand the problems thoroughly, just like everybody else at the time. But one thing that bothered me a lot was I didn't have a language that allowed me to express my solutions. And so you need to deal with hardware. If you're building an operating system, you need to write process schedulers, you have to write device drivers, you have to write memory managers, things like that. And you need to raise the level of abstraction so that you can talk about this piece of code and that piece of code, not necessarily on the same machine. How will they communicate? They may very well not have any shared memory. So that was my problem. And I found at the time there was no language that could do both. However, there were many languages that could do half of this problem. And so I picked Simulant for the abstraction mechanisms for the high level stuff. This was where we got object-oriented programming from. And I picked C, partly because it was one of the 20 so languages that could do the job, and even more because Dennis Ritchie and Brian Koenig was down the corridor for me. So I had absolutely superb support. And we're still going on with this idea of being able to do really close to the machine stuff for efficiency and being able to use hardware and high-level abstraction to get away from the mess that it is down there. One of the things that allows you to build something interesting is to be in a place where you have some support, be part of a community that is doing interesting things. And Bell Labs at the time was simply the best in the world. There was nowhere like it. And unfortunately, there's nowhere like it today. But there was great people there. See some pictures there. You may know of them. You may very well not know about Doug McElroy, but he was the guy that we all went to when we had problems. A fair bit of C++, a fair bit of Unix was invented on his platform. So we had a huge range of technical problems because we're dealing with the communication system and among other things helping run the North American telecommunication system. And we had a rich technical culture that had well 6 or 8 prize winners and that kind of level. And they had a notion of what it was. They wanted to do innovation. And innovation was seen as invention plus development. Just having an idea, just writing an academic paper was not enough. If that's all you do, you have to be very good to keep your job there. But if you can make it into something real that helps people that use help develop things, that's good. So innovation is invention plus development. So if you want C++ and 2 lines, it's still what I said earlier. It's a direct match to hardware. It's zero overhead abstraction. And in the future, we want to handle newer and better hardware better. And we can do hashes, more suppose, GPUs, FPGA, SIMD, that kind of stuff. We're doing a lot of it. And the stereo overhead abstraction, we started in classes for software, these softwares, and did all the other things. Generic programming was sort of finished finally after 20 years in 2020, when we got concepts in to express and use constraints. And all engineering relies on feedback. There are people who complain that C++ is changing, but of course it was meant to change. There's no way that one guy, could design the kind of general purpose programming language that I wanted. So I had to do the standard engineering thing, which is you do the best you can. You try not to close any path to the future that where you want to go, and then you build it. You try it out probably at scale, and then you fix what wasn't done right, and things like that. That's standard engineering. That is feedback. And one of the rules of thumb was that had to rely on real world problems. There's always theoreticians, mathematicians, computer science guys that comes and tells you what you have to do. And my defense in the past and still is to go and see what problems people really have. So I travel a lot talking to people who build interesting things with C++. So you've got an engineer there. That's the machine that makes all your hardware programmed in C++. All the high-end hardware, and there's some applications there. Okay, and C++ did evolve over the years. We started there and we're up there. And if you're interested in language features, you can look at a slide like this and see when they come in. And YouTube and books and such are full of explanations of it. I am not going to try and explain everything. I want to have a little bit of time with Q&A to see what you're interested in. One thing that I find that a lot of people don't understand, and, especially students, they can't understand why we can't get what we really want just now. And the point is that most organizations that use programming, use software at a large scale, lasts for decades. In fact, the only reason that you can trust that something like C++ will work in 10 years is that there's still stuff from 10 years ago that worked. Somebody was really interested in compatibility, not just the latest fashions come and go. If you go back and look at the languages that were fashionable during C++'s lifetime, you will find that most of them are dead. And that's not good. And just rewrite all the code the way they said when they invented Java. It just doesn't work. Java was lucky that there was a field for which C++ wasn't defined. C++ was defined to handle a certain class of problems, complex problems that required high efficiency access to hardware. That's not what Java does. And I shouldn't say anything bad about Java because with Java is a C++ application. I mean, what do you think you write the Java virtual memory? And why we're added most of the Python underlying stuff and all of the JavaScript stuff. So anyway, it's you have to find the right problem and things work, and then you have to keep stability in that field, not trying to be everything for everybody. I used to go around saying I want C++ to be the second best language for a lot of things, not the best language for everything. That's absurd. The point is that you can always build a special purpose language, a domain-specific language, if you can define your domain and do it better than anything else, because a general purpose language has to be more complex to handle more things. So the foundations of C++ is relatively simple. I like static type checking. I want equal support for built-in types and user-defined types. That started from the very beginning, the first couple of weeks. And by the way, that is the foundation of generic programming. And we have to have both value and reference semantics, because value semantics is the ideal, easiest to use, easiest to get right. But you have to have reference semantics pointers to implement those abstractions. And then systematic and general resource management. If you have a spaceship, you can't send a repairman. You can't send a repairman to L2, where there's some code up there. And efficient object-oriented programming, of course, flexible and efficient generic programming, of course, but a lot of people don't get it. There's a lot of compile time programming in C++ these days. If you can do the stuff, compute it at compile time, you don't have to waste runtime to do it. And that has been very, very useful for many fields for a long time. And then direct use of machine and operating system resources. So a language is not just a language. Nobody writes code in just the reference manual. You write code in a tool chain. And so you have to look at the various parts of the tool chain and see what can be done. The language is a central part, but it's not the only part. We have standards of the development communities. Communities are important. Industrial use, research, data. That picture, by the way, is a picture of the standards committee celebrating C++ 20. Now, we work with consensus. How do you get these guys to agree to anything? That's not easy. So, little bit of politics comes in, so intelligent. So basically, the result of all this is that we have code in the world and way beyond. Let me see. I think that's the second most powerful computer on Earth. I didn't know that the matrix was written in C++. It is, and there's other stuff. That one is out. It's L2. Since you can't send a cameraman out there, this is a fake picture, but fine. Okay. And good software is invisible. Most of what we rely on today, including a lot of the stuff in your pocket, you can't see. So I just put some samples up there, some logos, and well, have a little bit of that. Everything. And then people ask me about the future. I welcome, because it's hard to predict, and I prefer to talk about things I know something about, and sort of the world 10 years in the future. Well, I don't know anything about. I'm not going to answer any questions. But if you want something good, you need gifted individuals with families. Usually, they are in a local culture and great locations. There's great locations. Cambridge is two I know of, one on each different continent. Bell Labs was great. Silicon Valley, there's a lot of stuff out there. And you need long-term stability of what you're doing. Otherwise, it comes and it goes, and it's a bit of a nuisance to see one's work being dismissed. And computing is not one thing. I really wish that education would focus on different things. It is not the same to build an app for the phone and to build the infrastructure that something relies on. I mean, Gilder van Rossen wanted to write Python so everybody could program, and he succeeded. He's a nice guy too. And I didn't want to do that. I wanted to write a language that was great for engineers building tough things with constraints, including reliability constraints. I do not want everybody to program the brakes of my car. That's a job for
that you don't want everybody to program the brakes of your car.
What do you think your brakes are programmed in?
What are my brakes programmed in?
Well, if you're using a Mercedes or a BMW or a Toyota, they're programmed in C++.
The brakes of the car are programmed in C++.
Also, got a coffee machine is programmed in C++. And I know somebody who's doing the power supplies for laptops. It's everywhere. You don't see it. As I said, good programming is invisible. Okay, we're switching to Q&A. You already had the first.
Yeah. First of all, thank you for your presentation and for your time. Is C++ what you envisioned it to be? Like
C++ has the major parts that I wanted. And every one of those parts could probably be done better with retrospect. But you never have retrospects. This is building, and you start, and sometimes you get stuck with stuff you would rather have seen otherwise. I'm working on something called profiles, which is what you can specify basically which subset of a superset that you want to program in. You need a superset so that you can get your libraries, your abstractions with that actually are implemented using the stuff you really don't want in your application code. So I'm working on that problem. But I would say that C++ 20 and to parts of C++ 26, which is being voted on right now, is very much what I was dreaming about. Not precisely, because of course I couldn't, but sort of the general thing. The idea is you want something like that, and then you spend years working out what actually can be done.
thank you.
What are your thoughts on upcoming programming languages like Rust?
There's always new languages coming on. Some of them succeed, some of them don't. I've been in this business for a long time and not treated it as a business. I've just concentrated on making things better for my users. I don't see anything that can do as much as C++ does, as well as C++ does. But as I said before, you can always build a particular language solving one problem better. So Rust solves the memory management problem. But that's all it does, plus some modern syntax. And if it succeeds, which it probably does, it will grow in size. I said the same with Java when that came on, and it tripled in size. And then this stuff about simplicity disappears. I want safety, but traveling around, I found that different people want different kinds of safety. I don't just want memory safety, I want resource safety. Memory is just one fairly simple resource. I can crash a system by leaking file handles or locks much faster than I can crash it with memory. If you look at my readings, you can see I know how to handle memory and resource management. Other people want guarantees for performance. That is, they want a job done in 10 milliseconds. If you're dealing with engines, if you're dealing with wiggling wing chips and such, the safety issue is not memory. It is some physical constraints on the thing. So yeah, I would like safety, but I want much more safety than Rust would give us.
What are your thoughts on AI in the future of computer science?
I get this question a lot. Or I'm not an AI, and I don't plan to become one. Secondly, there are so many promises, and I've heard some of them before. So I'm skeptical. I'm not saying it won't work, but I'm saying we don't know where it will work yet. And secondly, you quote the ECNA, the idea of programming in English. stew. So we have to figure out how to deal with the LLMs. We have to figure out how to express prompts because at least it's interactive more than it was in Deister's time. And finally, I think we really need something to put limits on. I know there's people who built LMMs to kill the military, but for a lot of the things we do, we would like to have some guarantees like rules for robots that says they mustn't harm. And we don't have those yet, so we should work on that. Yeah, probably already said too much. So, thank you.
If you could have a magic wish with which you could remove the backwards incompatible change and all existing code would magically be fixed, what change would you make?
One, it's impossible.
Yeah.
If I had, it's impossible because people are relying on things that really cannot be validated as being correct. But if I have a time machine go back, I would not pick the C syntax, especially the declarative syntax. People are very proud of being able to make a function returning a pointer to function, returning an array and such, and you shouldn't be proud of such things. It's like typing a Scandinavian language on an English keyboard. Nobody should be forced to do that. Secondly, I would like to stop conversions of built-in types both ways. The idea of having a long implicitly turn into a character is not a good idea. But it never was a good idea. I tried to solve it back in 79, 80, and basically the Unix group told me that if I did that, I would never get anything else done. And I would have a language. And so I actually wrote a generic program that solves that problem. So if you go to my publication list on my website and look for my latest paper for concept-based generic programming, you will see how you can solve that problem in, I think, 42 lines. So, but anyway, you can't change the thing. So that is my main worry, main concern. I still feel sore that I was stuck with solving it 40 years ago.
Well, thank you.
I was just reading recently that Tony Hoare, who came up with the idea of the null pointer, has regretted that. Do you have any comments on that?
Sure. He was overestimating his own importance. There was always null pointers because those null memory addresses. He didn't invent it. He put it into the language. And we can argue whether he should or not. But if he hadn't, his language wouldn't be used for writing things like Linux. We needed those null pointers. And so it's one of the few cases where Tony is true academic. He is like the early computer scientists dealing with languages, actually somebody who built practical systems as opposed to not everybody in academia. But I think we needed it, but maybe not for the kind of applications he wanted to look at. We have ways of dealing with it. You look up the C++ core guidelines, you'll see I have a null pointer class that basically makes sure that your pointers aren't the null pointer.
So one of the most annoying errors I get when trying to program in C++, which I've only recently learned, is that I'm being told that a file does not exist.
Yeah.
So so as a developer of C++, how did you handle programmers having file troubles? What files came with?
Use the file system library. There's the file system library for navigating class hierarchies, and I use IO streams that for files.
Oh, so there's a file system library that contains all the files that need to exist for a program to run?
No. It all goes to the operating system. If you tell you want to open file foobar for reading access, it will go to the operating system and see if there is such a one.
When you try to use a file or something that needs a file, it goes to the operating system?
Yeah. I mean, the operating system owns all the files.
Yeah.
I mean, that's been there for forever, even before Unix.
What's a part of C++ which you think developers misunderstand the most?
Sorry,
What's one aspect of C++ which you think developers today misunderstand?
Okay, what's the thing people most misunderstand? It's not one thing. Different communities misunderstand different things. There are people who think that they should write C as if the world has stopped developing in C++ in C 9. And apart from that, essentially all modern C is C++. If you go to KNR, Kernighan Original 2, every single program in there was tested in C++. The syntax is. Then there's people who think that everything should have been Java. That is, everything should be class hierarchies. But I never could see why squared and to be part of a class hierarchy. I don't want to say 2 dots squared. And it gets even better when you have complex scale square roots. And then there are people who think everything these days could be template metaphor, which is also wrong, but should do better. The point is that you have to look at your problem and then see what kind of style of programming you want. And you shouldn't get stuck in some part of the past and get fanatical about it. Passions change. And if you pick just one subset, the fashion will change away from part of your subset sooner or later.
I was just wondering, what's the defining quality of a language you think that makes it stay? Like, there are languages, like a few years ago, I heard about the language called Julia. Which I heard a lot of good thing about it, but then it just, I don't know, faded away or didn't come to mainstream at all.
Yeah, I was looking at Julia 2 weeks ago, trying to understand it a bit better. And I think part of the problem was that the people who built it was stuck in a bubble at MIT, a bubble of scientific programming people. And their shows, they compare to Java, they compare to Fortran, they compare to C, but it was really old C. They mentioned C++, but they clearly didn't understand what they were talking about. So I think it is a case of people doing really well in a limited domain. It's sort of the domain-specific language I mentioned. Fortran is a domain-specific language for dense linear algebra. Julia is a more modern version of that. And what happens is that you get this perfect language, and then you are in an organization that needs to do something else. My main example is CERN. They obviously need to do heavy-duty scientific computation, which Fortran and Julia might be the best solution. They also need graphics because they need to visualize and get the pictures moving to show what was going on. And Fortran Julia is not particularly good at that kind of detailed graphics. Then they need to control experiments. And they need to control experiments with precision that goes beyond what we can imagine. more details than picoseconds. And then they have physical controls, like I was talking to a guy there whose job it was to close the big heavy doors when they were shutting down the system. Big heavy doors as some tons of lead. Starting it is hard, stopping it is harder. Okay, so you need a general purpose language unless you want in at least 5 different languages that are ideal for each of these, and then they have to communicate. And then the developers in those languages have to communicate, and you know how common language wars are. They don't communicate very well, and that's not good. So the strength of a general purpose programming language like C++ is that it can do more things than you possibly want. Or me. Yeah.
Thank you, Professor. Sorry, to interrupt. We have one last question though from a remote site. Okay, that wanted to ask. So Zach, if you're around, can you hear us? Can you ask?
Yep. Hey, can you hear me? Yeah. I'm sorry.
No? Want me to ask? Okay. Comes from the Northeast, and they said, what is the one thing you hate most about object-oriented programming?
That's relatively easy. Overuse. People who think everything should be part of a class hierarchy. I want my complex numbers to be compatible with Fortran because there's a lot of really good Fortran libraries that I want to use. I do not want it in a class hierarchy so that I can redefine the meaning of a complex thing. Because we don't redefine the meaning of a complex plus every century. Don't overuse it. If your domain is hierarchical, use object-oriented programming the way Christian Nico and Johan Dahl envisioned it, and I did my implementation of it, but don't think it's for everything.
Thank you, Dr. Stubb. Okay, thank you very much. That was wonderful. I hope everybody enjoyed it. I think at this point, we are going to separate into our individual regionals. So Greater New York, we're staying here. But we're going to say goodbye to the Northeast and East Central. Bye guys. Bye guys, and good luck. Give them a second to drop out, or we're not done here. Now we're doing our opening here. Okay. So first thing I would like to do is introduce our site director here at Columbia University, Christian Lim. He's involved in multiple ICPC initiatives and groups. I have no idea how he gets all this stuff done. So, Christian, come over here and give us your secrets.
Yeah, hopefully this works. All right, so I guess who is anxious to win? Can you raise your hand? Everyone? No, not everyone. Right. Wow. Okay. Anyway, it's really important today somehow in this room. So all I want to really say is thanks a lot, everyone, for coming to this contest. For sure, for some of you, it's been a long way. For others, it's very short, dorm. But either way, you guys all made it here. What matters is you come here to have fun, feel empowered to do the best work possible, and then go home with the crown of the day. So with that, I want to end. But I guess congratulations for being here, and best of luck. Yeah, thank you, everyone.
Thank you, Christian. So I just want to introduce our Greater New York team. These guys have done so much work to put this all together. So of course myself, with Christian, who just introduced, with John Buck, the Systems Director and Chief Judge here. Fred Pickle, the judge. Ute and Samuel are in systems, and, along with Chris Lent. And Grace and Holly have been helping out a lot with operations. So thank you for me to even dedicate. Okay, so we're almost done, I promise. And so now we're just on to some business here. So at this point, all your electronic devices should be safely stored in the classrooms. If they're not, they will be very shortly, I assume, unless you want to be disqualified. There will always be a proctor in the classrooms. If you forget to check anything, you can give it to your coach, or when you get back to the room, just put it in the corner. Once you're back in the classrooms, you can sign into the contest. And I don't see John Clevenger here, but he would say, do not touch anything. Once the contest starts, there is no talking except to your teammates. You can all spot however you can talk to anybody else wearing a red shirt as staff. You may not talk to any coach or any other student that is not on your team. Anyone found doing so will be disqualified. The entire team will be disqualified. Note about possible ties based on the number of problems solved and time to solve. The tiebreaker is that if the situation happens, the tiebreaker is the first to solve the last problem. After the contest, please make your way into the central area here. We will have pizza, and you can commiserate a bit. And also, we will have Jeff Brains back in here with Rope. We'll be back in here to answer any questions that you may have while the judges and the systems team puts together the resolvers. So that might be about 20 minutes. So if you have any Q&A for Jeff Brains while they're here, it'd be an excellent time to ask it.
I don't know.
We will be giving out medals for first, second, and third place. Additional medals and prizes from Jeff Brains are also up for grabs. We also have 3 copies of Dr. Shawshup's book that will be awarded to the team that answers the most problems correctly. Gives it a C++. Of course, we also have the Greater New York Championship Cup that was returned to me from Rutgers this year. It's a perpetual cup, and it passes from school to school depending on who wins that year. When you win, we add a nameplate to it, and you get to display it at your university for just under a year, and then you must return it back to me to do this whole thing all over again. At this point, I'd like to invite our head judge, Chief Judge John Buck, up here to say a few words. And if you have any technical questions, now's the time to ask before we have everybody go back to their classroom. John? All right.
Everyone can hear, hopefully? Good. Glasses on something suit. Okay, so this will probably be more of a technical briefing than a judging briefing, but we'll answer questions about the judging as well. So let me go over a few things first. Well, anyone that had a pink ribbon drive, they've all been confiscated while you were here. We went through and removed them all. And you should find a green one on your workstation when you go back. You'll have to boot that up. So everyone should have a green one when we go back. If you're not use the pink ones, they won't work. Okay. And when you go back to put it in, boot it up. Okay. Log into the desktop using your credentials on the sheet that say real. It's practice and real. Use the real ones. And then you can log into the team interface. The contest interface. You can log in. The second one's using the same credentials, but then do not anything at that point until the contest starts. at 11:15 promptly. Because we're in sync with the other regions, okay? That's about a half hour, 20 minutes from now. So you're gonna go back, load up your computers, and then just sit there and wait. Okay, and we're gonna deliver the problem sets. You can't open those until 11:15. And the proctor will say when that happens. At that point, you can go to it for 5 hours. The people that have to use the Mac stuff, if you did it before the break, that's great. If not, you're gonna have to, get your system booted in 20 minutes or whatever it is. If not, you're gonna have to run into the beginning of the contest. I mean, we did this, we had the practice open for 3 weeks prior to the contest. So you get familiar with how to do that. Many people did it. I mean, I think probably 16 people that are using Macs actually logged in during the practice and successfully did. So this should be easy. You just have to redo the same thing, creating the virtual machine on your Mac, and off you go. People that have PCs, it should just be a matter of plugging it in and booting it up, and off you go. Printouts. I'm gonna go back to the thing. External devices. You're not allowed to use bring any external mice or keyboards unless they've been approved. If you send a request yesterday or the day before, they haven't been approved because you had 3 weeks to do that before the contest. So you cannot use those. You certainly cannot use anything wireless. No wireless mice, no wireless keyboards. No mice that have programmable buttons, no keyboards that have programmable buttons. Okay, basic mice and basic keyboards if you did bring your own. Right, no external monitors, obviously. See, printouts. The printouts we didn't have enabled during the practice. They will be enabled here. You're limited to 10 pages per hour. Okay, so keep that in mind. You should only use the printouts for listings. Do not do not print PDFs. Do not print web pages on them. Okay, you just print source code. And maybe if you have short outputs from your run. Because the printers, we have 2 printers for all these people, and we have to have people delivering them. Some of you are on the first floor, the printers are here, so it might take some time. Be patient, don't keep resubmitting it. You use it. If you have a problem with the printouts, after you submit it and have it come for a long time, like 10 minutes, talk to the proctor and we'll see what's be going on there. And printers could be down or something. So really just use them for printing source code listings if necessary. Problem sets will be passed out, like I said, by the proctors in the room, and don't open them until 11:15. There are going to be 12 problems. And the first problem A will be the easiest one. And our Greater New York region, and we also that East Central, also Northeast. So problem A be the easiest. So you're urged to look at that first. And yes, that's it. Any specific question?
Everybody quiet down, come on.
The clarifications too. If you have any questions, submit a clarification. It's available on the web interface. Okay. And we'll try to answer those in a timely fashion. Some of the problems were written by judges in the other regions. So if you ask a question that we didn't write the problem for here, we have to submit it to them and they'll get back to us with an answer. So it might take a little longer. But the problems that were done here, I think we had 4 of them that were done in Greater New York by our judges here. So we'll get back to you on those. I think they were, well, I can't tell you what they are. And Joe said anyone with a red shirt you can talk to. You can also talk to me and Tom because we have black NAC shirts on with our championship shirts. Okay. And John Clevenger, who was the guy you saw on the board, technical director. Is there, and now are there any, you have something saying?
Just any proctors that are here, they know we signed multiple proctors to the room, so please at this point go back to your rooms that you were assigned to.
Proctors, yeah. The proctors, the contestants stay here. Okay, it's a question, I will answer it. Our
Communication is as soon as it's shared all and not this.
right, if it's a specific question about a problem and it doesn't affect, if it's a question that doesn't affect the section of the problem, like, so a lot of questions we answer, no answer, or read the problem. Those will not be shared with everybody. But if there's a clarification that's needed, the response will be shared with everybody. So we say, you know, well, this test case is wrong, and we find out it is, which they're not, by the way. If you see it's wrong, we will share it with everybody.
You're not. Jim said something, okay, you want to test it. Or is there electronic equipment somewhere, or coach is supposed to collect that?
Yes. Either or. They can give to their electronic devices, but we have proctors in the room and they're gonna be in the room for the most part.
Just put it in the back.
They put it in the back or along the side, and then they can collect it when they leave. They just can't have it next to them.
Right, we only allowed to use one computer, by the way. I noticed that on somebody desk, there's two computers, you're only allowed to use one. And if you don't have a green drive, when you get back, ask the proctor to move, they have extras. Right now, you're gonna go back to your rooms, and you're gonna boot up the drives.
All right, hello everyone. We are live. Welcome. This is the ICPC North America East Division 2025 competition. We're here with teams from the ICPC Greater New York, Northeast North America, and East Central North America, competing for glory and a chance to qualify for the North America Championship. The contest will start in about 30 seconds. It should be pretty competitive. And once things get started, we'll talk more about the format, the problems, how things are going, qualification for the North America Championship, and so on. And the contest is about to begin in 5, 4, 3, 2, 1, and we're off. So let's pull up the scoreboard real quick. Cool, so we can now see the problems are go through L. The teams have been told in advance that problem A is going to be the easiest. So we should expect to see submissions on that one relatively quickly. Other than that, the order of the problems is not fixed, or they will not necessarily be ordered by difficulty, and so we'll just have to see how things go as the contest progresses to get a sense of which problems teams think are particularly easy or difficult. As the submissions come in, we'll be able to see them in the queue on the right. We'll be able to see whether the judges, as the automated judging system reviews each submission, we'll be able to see whether it's accepted or rejected, and if it's rejected, what error the teams ran into. Hopefully within the next few minutes, things should get started. Music is still playing. Let's pause that. You'll see we have, don't know the exact number, but over 200 teams, I believe, here. This is one competition for the North America East Division, but it's split into the 3 regions: Greater New York, Northeast North America, and East Central North America. The top teams from each of these divisions will qualify for the North America Championship. Each region is guaranteed to have at least 3 teams advancing. These will be the top 3 teams in each division that do not come from the same school. So if the first and second place teams in Greater New York, for example, both come from the same school, then the 4th place team will advance instead. In addition to that, there will be some number of wildcard slots awarded to the top teams from the combined scoreboard across all 3 regions. They'll be awarded to the top teams that did not qualify by being in the top 3 of their specific region, and those teams will also receive invitations to the North America Championship. Last year, I believe there were 8 wildcards. We have no guarantees as to how many there will be this year, but I do think it is safe to expect that there will be at least a few, since the East is a particularly competitive region and tends to receive a substantial number of slots in the North America Championship. All right, so we are still waiting on that first submission. We're about 3 minutes into the contest, so we should expect to see that coming any minute now. It's always an advantage to get off to an early start in ICPC because of the way the rankings are determined. So we have 12 problems here, and the team's goal is to solve as many of the 12 problems as they can. But there will be some ties. And so, hold on, before I go any further, there is a submission from Michigan State University Spartans on on problem A. Let's see how it goes. And they get accepted. So congratulations to Michigan State on the first solution of the contest. And Yale right behind them, also with a submission to problem A. And that is also accepted. So Yale right behind them. Rutgers coming in as well. We're now starting to see lots of submissions to A. SUNY Stony Brook attempts A but gets wrong answer. Toronto Metropolitan University also attempting A. They get it right. Princeton Team 2 gets A. Brown University, Waterloo both attempting it. Just to go over what you're seeing on the right hand, So again, as these submissions are coming in, you can see they'll light up either in green or red as they're accepted or rejected. The letters AC stand for accepted. Submission marked AC was approved by the judges, and those teams will move up on our scoreboard. You've seen some teams getting the verdict WA, that stands for wrong answer. Teams that get wrong answer or had their program rejected because the output did not precisely match what the judges expected. A tricky thing about these competitions is that even small errors like outputting a single extra character that wasn't expected by the problem will cause your submission to be marked as wrong. And so it's pretty punishing. Have to like exactly match the expected output for every possible test case in order to get accepted. You can see teams are handling this problem quite well. Already a dozen of them have gotten accepted, still just within the first 5 minutes of the contest. Cornell, McGill, Yale all have pending submissions. McGill gets it correct. And maybe just to chat about what you see on the scoreboard real quick. So the rankings are determined as follows. So first you can see this number sigma, that's a 1 for most of these teams at the top. That represents the total number of problems solved, which is the first tiebreaker. Any team that solved more problems than another team will always place ahead. The second number under penalty is a little bit trickier. A team's penalty time is the sum of their penalty for each problem that they successfully solved, where that penalty is defined as the number of minutes into the contest when you solve that problem, plus 20 minutes for each incorrect submission you made on that problem before getting accepted. So here in down at in 24th place, you can see McGill has a penalty time of 25 despite having solved A in 5 minutes because they had a wrong submission first. Also worth noting, Purdue Fearless solved F first and was quickly followed by a couple of other teams. So even though A has been designated as the easiest problem of this contest, F appears to be relatively straightforward as well. So we'll continue to see whether teams keep going for problem A or transition over to attempting problem F. Now that more teams have started solving, I'll zoom the scoreboard so we can see teams outside of the top 25 or so. Yeah, so you can see right now McGill and SUNY Stony Brook are at a significant disadvantage on the scoreboard based on taking a penalty on problem A before getting accepted. That said, like as the teams solve more and more of the problems, or the 20 minutes that they lost now, while a massive disadvantage from the offset, will become less of an issue as they move forward. And Michigan State just became the first first team to solve 2 problems by getting accepted on problem F. So now they have 2 problems solved with a penalty time of 10 minutes, which puts them in a strong position at the start of the contest. But again, an hour from now, a penalty difference of 1 to 2 minutes is unlikely to become particularly significant in determining the standings. So we're still going to have to keep going and see what ends up happening. The teams do seem to be converging is on A and F as the 2 easiest problems here. So those are the only ones I believe that have received any submissions. However, it's also possible that there are other problems in the set that are just as easy, but that the teams haven't read yet. Maybe the description is a little bit longer and it's harder to realize that they're straightforward. Overall, though, lots of teams having success on A couple of wrong answers, but mostly people are doing pretty well on this one. And MIT just solved A. They are now the second team to get to 2 problems. Looks like Rutgers Likely AI is also attempting A. It does make some sense that the teams solving F, which according to the judges at least is slightly harder than A, are now having some success going back and solving A and then getting to 2 problems relatively quickly. And so yeah, now 5 teams have solved A and F, so these appear to be pretty straightforward. Most of the teams are likely to solve these relatively quickly. Still remains to be seen, though. Once you have two problems, what do you go for next? Now, about 70 teams have solved at least one of these two problems. So we're off to a pretty strong start. That's roughly a third of the teams in this competition. MIT let me submit going for their second problem, and they get it, moving up into 6th place, I believe. If that's a 6 or an 8. Yeah, you can see actually in the queue, MIT submitted both of their two problems in short succession. So it looks like they were in some capacity working on them in parallel. But now MIT has been passed by a couple of other teams just by having solved one of the two problems faster. So even though they got to two problems more quickly than, say, University of Toronto or Columbia, they're ranked lower because their total penalty time is worse. So that's why it's so important to get on the board early. Is that like once you solve the easy problems, the timers on those stops ticking up, your penalty time is locked in, and so you can afford to take slightly longer on the hard problems and still do well. More and more teams getting to two problems. We have 10 teams that have solved both A and F. Still no submissions at all on anything else. So more and more teams are solving A. We now have over 100 teams that have solved at least one problem already. So really quick progress on this competition. Also goes to show you, does take some skill just to even start solving these problems. You have to write a considerable amount of code, set up your machine. And so given that, it's pretty impressive that so many teams have just managed to get on the board all this quickly. And we now have our first solution to a problem other than A or F. The team from, I believe, let me double check this. Go back to the top of the scoreboard for a moment. The team from Brown University has solved problem D. They were the first to solve it, so congratulations to them. We'll see whether other teams view that as the next most approachable problem. All of these all of these top 10 teams that have solved two problems already have to be working on some problem as their third one. We'll see if they also chose problem D or if they went a different direction. Still more problems still more teams reaching two problems. No one else has attempted D yet. It'll be interesting to see if Brown now they're at a bit of an advantage knowing that F is a straightforward problem, and we'll see if they can leverage that to get to three problems faster than the other teams who might take longer to realize that D is a pretty straightforward task. Seeing more and more submissions. We're up to over 20 teams on 2 problems already. So again, things appear to be going pretty well so far. See, Purdue down in 118th place could move up quite a bit if they get F correct. And they do. So they move from 118th to 23rd. Again, that's another team that took a little bit longer to solve or to get their first problem A, but now by solving a second problem quickly has managed to do quite well for themselves on the scoreboard. All right, so Yale, now we have another attempt on problem D. This team has not solved problem F yet, so even if they solve it, they won't be the first team to 3 problems. But they do get accepted, so they now have 2 problems solved already. Let's resume the scoreboard, and we can see how things are going outside of the top 25. Got 130 teams. That should be a little over half of the competition, I believe, give or take, with at least 1 problem solved. Rutgers attempting, or another Yale team just got D correct. Rutgers attempted D as their second problem, but got wrong answer. Still, I believe nobody who has attempted a third problem yet. So we'll see. I'm guessing that we'll see that within the next minute or two, especially as the teams on 2 problems now know that D is pretty accessible. And yeah, Waterloo is attempting to solve D. If they do, they'll move into first place as the first team on 3 problems, but they get it wrong. University of Toronto attempting G, so they'd be the first to solve if they got that right. Let's see how they do. But it's wrong answer, so no luck on G yet. Could be that it's an easy problem and they've just made a slight mistake. It's also possible that they've or that it's a bit of a tricky problem where you might like think that there's an easy solution. It turns out to actually be more challenging. Michigan also thinks G is accessible. They've got a submission running. Let's see how they do. And they get accepted. So Michigan State University is the first team to solve problem G. It's a great performance for them, combined with also having the first submission of the entire contest on problem A. And so now they're in first place with a very strong penalty time, being I think the first team to get to solve a problem, first team to get to 2 problems, and now first team to get to 3 problems. So they're in a very strong position so far. Still seeing more submissions on A and F, as well as D, but a couple of teams getting wrong answer on D, so seems like there might be a bit of a trick here in some way. You can see things have slowed down a little. Teams are we now have about 150 teams with at least 1 problem solved. Still no teams other than Michigan State on 3 problems. But as I say that, Purdue attempting their third problem D, and they get it right. So now they're up to 3 problems with a worse penalty time than Michigan State. I do think Michigan State's success on G is likely to motivate Purdue to look at that problem next. Likewise, Michigan State, I'm sure, is working on D right now. So one interesting thing about the contest format is that all of the teams can see the scoreboard the same way that we do. So all of this information is public to them. And so that means that the teams can monitor how the competition is going, see which problems other competitors have solved, and then choose which problems to attack based on that. And so even though the problems are not in order of difficulty, and it can be tricky to figure out which one is easiest, for many of the teams, all of the ones not at the very top of the scoreboard, you can sort of figure out the difficulty ordering just by looking at what other teams have done. Toronto is now attempting problem I. We'll see if they get it right. There's lots of different choices for the third problem so far. We'll see if their submission is accepted. Give it a moment. Still more teams attempting A and F. Toronto's I taking a while to judge, and they get it right. So they're the first to solve problem I. That is the 5th problem overall that has been solved in this contest out of 12. So I would expect that the first hour of this contest is going to involve teams roughly trying to clean up this set of easy problems, maybe 1 or 2 others, until they got on to the more challenging tasks. So now we have these 3 teams. Notice that University of Toronto, despite solving I several minutes after Purdue solved B, or they were faster to their earlier problems, and so they have a slightly better penalty time. Michigan State still has a pretty comfortable margin at this point with 9 penalty minutes over the next team. Again, anything can happen from here. Carnegie Mellon is attempting G. Let's see how they do. They get it right. So congratulations to them. And Purdue Fearless just passed Purdue Hyperbolic Latte by 1 minute, solving D. Polytech 3 just solved D. So we're now at 6 teams on 3 problems. Expect this number to grow substantially. It does look like ADF is the most common triple so far, and Purdue Frosted Entropy joining them. So 3 out of the 7 top teams right now are from Purdue, all with the same set of 3 problems. Of course, different teams from the same school cannot collaborate, but it does look like they're applying similar strategies. MIT is attempting problem I. That would bring them to 3 problems. They had a great penalty time on their first 2, so if they solve this, they'll be in a pretty good position. I think their total penalty time would be 36 minutes, and they do, so it's enough to bring them into 3rd place. They're tied with Toronto on penalty time, so the tiebreaker between 2nd and 3rd is the time at which the last problem was solved. So since Toronto got to 3 problems before MIT, they are ranked above them on the leaderboard. One thing that's interesting to note about the state of the scoreboard right now is that even though D is the 3rd most solved problem, all of the top 4 teams solve problems other than D as their third task. Which I don't know, hard to tell what to interpret from that. Like, one possibility is that D is a problem that like is straightforward conceptually but takes a little bit longer to do, while G and I, if you like see the trick, are pretty quick to type up. And so the top teams want or tend to prefer to solve problems that might be like slightly conceptually more challenging, but that will take less time to implement once you have the idea down. And so those teams like might be, and so it's possible that might apply more to G and I than to D. Right, so now that we've had a couple of minutes, I think, I'm trying to remember, I think it's been about at least 5 or 6 minutes since Michigan State has gotten their third problem. So now we should be in a pretty good position to see a team getting to 4 problems before too much longer. Should be exciting to see. So I think somewhere in there we've seen 1 submission on problem H. Other than that, we've only seen problems on the 5, only seen submissions on the 5 solved problems. Show some statistics real quick. Almost 200 teams have solved problem A. So again, really strong performance there. G, well, Waterloo just became the 4th team to solve it. D has 19 solves. Again, many of those are teams that are not, that have only solved 1 other problem. Columbia attempting F just got their 3rd problem. University of Michigan already in 28th, which is pretty strong, but they're attempting G, can move up even further if they get it accepted. They do, so University of Michigan now in 12th place. Congratulations to them. Still more and more teams attempting F. Definitely like more wrong answers on this one than on A, but teams are still but I think most of the teams are likely to get this one figured out by the end. We did just see in the sidebar a rejected submission labeled RE. That stands for runtime error. So that means that like the program crashed due to some error, maybe like dividing by 0, accessing an array index that was out of bounds, that type of thing, before output or instead of outputting an answer for one of the provided test cases. Usually runtime errors are on the easier end to debug just because it's a lot easier to answer the question of like where in my code do I like access the wrong array index, for example, than it is to figure out, okay, why is my solution wrong? And so typically when you see a runtime error, you should expect the team to figure it out and resubmit before too much longer, but we'll see if that happens in this case. All right, Michigan State now attempting their 4th problem, going for a problem I next. Seems like a reasonable choice. Other top teams have solved it. Why can't they? Give it a go. And they get it. So they get accepted on problem I. They move into 1st place with 4 problems, extending their already like pretty strong lead. Columbia moves into third place by getting D as their third problem. Still lots of solves on problem D already. Cool. So one thing that I'll highlight real quick is the you can see this is not what I meant to do. You can see some of the teams are labeled in gold. These are the teams that, if this contest ended right now, would automatically qualify for the North America Championship. So this means they're in the top 3 in either Northeast North America, Greater New York, or East Central North America. Now the one catch here is that multiple teams from the same school currently can be highlighted. Not sure if that's the case right now. It looks like it might not be. But again, multiple teams from the same school cannot qualify to the North America Championship. So if 2 teams from the same school do place in the top 3, the next one will qualify instead. As the contest goes on, we'll also talk more about what the wildcards might look like and what each team's chance of qualifying for the North America Championship might be. In the meantime, though, Waterloo Black attempting D, they already had 1 penalty submission on this, but this time they get it right. They move into second place. Because of their penalty, it will be possible for other teams that get to 4 problems to pass them, but for now, they're in second, which is a pretty strong standing. So Boston University just got to 3 problems by solving D. Got 25 teams now on 3 problems. And it now looks like A, D, F, G, and I all seem like their teams are having a good amount of success with them. A, D, and F, given the number of solves they have right now, it seems likely that most or almost all the teams will solve these by the very end of the contest, though some will obviously take longer than others. G and I seem like might be a little bit trickier, but it does seem like most of the teams are likely to do pretty well on these ones. MIT let me submit solving I. Or sorry, attempting I. Let's see if they get to 3 problems. Princeton just got to 4 problems by solving G. And now again, because Waterloo took that penalty submission, Princeton is now in the lead. It's worth noting though that even though Princeton now has a better penalty time than Waterloo, Waterloo has the advantage of they got to 4 problems sooner, and so now they have a few minutes of a head start working on their 5th problem. Toronto C is attempting B now, so I think this would be our first solve on that problem if they got it right. Let's see how it goes for them. And they get it right. So Toronto is now in 22nd. They're the first to solve problem B. That is 6 of our 12 problems that have been solved so far. Now again, Toronto's at a bit of a disadvantage not having 4 problems solved already, but it is nice that they now have a bit of an information advantage over the rest of the contest because they know that D, G, and I are all acceptable, while to the rest, are all relatively straightforward. While to all of the other teams, the fact that B can be solved quickly is news to them. Carnegie Mellon solve problem D. Ohio State solve problem F. In a couple of minutes, we'll probably start going over some of the problems, reading the statements, talking through some of the ideas involved. But we'll give it a few minutes to first to see how things are going. Purdue just got to 4 problems. Carnegie Mellon just got to 4 by solving B. So I think that's 2 solved we have on B now. Congratulations to them. And 5 teams on 4 problems. Looks like East Central has been pretty strong so far. You can see Purdue, despite being in the top 5, is not in the guaranteed NAC slot range. Those slots go to Michigan State, Carnegie Mellon, and Waterloo. So East Central are looking pretty strong. But again, if the scoreboard remains this way, the wildcard slots will be determined from the top teams not highlighted in gold, and so the top Purdue team and the team from University of Toronto look like if this contest were to end right now, they would be in a pretty good state for wildcards. Northeastern U just got wrong answer on B, so we'll see if they're able to debug that and get accepted. Yale attempting G is their 4th problem, as is that. 2 teams attempting G. NYU has been running on G for quite a while, so we'll see if they get accepted. Does look like, just given the state of the scoreboard, it does look like the judging systems might be running a little bit more slowly for the greater New York region. It looks like those teams are having their submissions getting held up. Although the scoreboards are going to be combined in the end, the greater New York region is running on a separate judging system from the Northeast North America and from the Northeast North America and East Central North America regions. And so it is possible that they're just having some system issues that hopefully will get debugged before too long. The university moved into 4th by solving G. Congratulations to them. Seeing lots of G submissions now. So teams do so as things have moved on, I think more and more teams have started shifting from to G instead of D. Let's see what the overall statistics look like. Yeah, still only 10 solved on G compared to 40 for D. Roughly, seems like the teams so far think that the difficulty ordering is A, then F, D, G, and I, but with some disagreement between various teams. University of Waterloo just solved I as their 4th problem. Again, it does seem like there are 6 doable problems so far in the set, so lots of room for so lots of room for teams to keep solving problems from here. Michigan attempting B, put them in a big lead on 5 problems. They should say Michigan State, but they get their first wrong submission on problem B. That'll hurt them a little bit, but again, their lead is large enough right now that they could still move or stay in a comfortable first place on 5 problems by solving B soon. MIT going for going for 4 solves. And not for a moment, now that we like see how things are actually going, we can talk about like who some of the favorites are going in. I think that most observers would say that MIT or that the MIT team Monkey is Typing is the favorite to win this competition. Their team members consist of 2 IOI winners, I believe, and then 1 who got a perfect score on the IMO. So, which is a pretty strong team composition. The ICPC problems require a combination of programming and math skills, and they have both those covered in spades. A couple of teams have managed to stay ahead so far. We'll see if MIT manages to catch them. One property about how regionals have worked over the last few years is because only 1 team from each school can qualify to the NAC. For some schools, and this tends to include MIT, Carnegie Mellon, Waterloo. It looks like Purdue this year, likely several others. It ends up being much harder to qualify or to be the top team from your own school than it is to rank high enough to qualify for the NAC, and so that can lead to some intra-school rivalries. Purdue, you can see we have their top 3 teams are 10th, 11th, and 12th right now, with Frosted Entropy ahead by 1 problem, but well behind on penalty time. So we'll have to keep following the scoreboard later to see. I believe the Purdue Fearless team includes at least 1, maybe 2 of their team members who got I think a bronze medal at the NAC last year. I'm not certain. Certainly a strong performance, qualified for the World Finals, as well as 1 team member who's been on the ICPC team at the University of Texas for several years before now going to Purdue for a graduate degree. So lots of experience on that team, but we'll see if one of the other teams from Purdue can beat them. Other than that, University of Waterloo are consistently strong. Carnegie Mellon is very strong. They, with a different team, got 2nd at the North America Championship last year. Harvard tends to be strong. Princeton, I'm not sure who the members of their top team are. Princeton 2 this time, but their previous team qualified to the Universal Cup Finals, I believe, which is pretty competitive. Oh, and MIT actually just moved into first, becoming the first team to solve 5 problems. They have all of the 6 solved problems so far, except for problem D, which is pretty interesting since most of the other strong teams did decide to do problem D as one of their first few. I guess there are a couple of teams on 4 that still haven't solved it yet. So interesting that they've chosen to solve all of these other problems before D. We'll see when they come back to it. But for now, MIT in first. Several other teams in position to pass them because of MIT's penalty on problem G. Oh, and Waterloo Black now moves into first just by 8 penalty minutes by solving I. Again, I believe still no solves out of these 6 easier problems. Here's attempting B as their 3rd problem, which is a slightly unconventional strategy. We'll see if they get it right. Also worth noting, we are still waiting on some of these submissions processing from Greater New York, it looks like. So once those go through, it is possible that we'll see some pretty substantial updates to the scoreboard. team MIT Let Me Submit is attempting to use their fourth problem. But they take a second penalty, which is a little bit unfortunate, but again, nothing that they can't come back from by the end of the contest. University of Waterloo Red now moves into second place with problem D just by 1 penalty minute. So again, like this is where things get a little tricky. Waterloo has the top 2 slots, but because they are these 2 teams are from the same school, they can't both qualify for the North America Championship. And so right now, the NEC slots would go to, or if the scoreboard stayed how it is, which is highly unlikely, the NEC slots would go to Waterloo Black and then University of Toronto and Michigan State for the North America East region. NYU Team 2 attempting E as their second problem to end up getting a TL, which is time limit exceeded. So in this contest, every problem has a time limit, usually something like 1 second, 2 seconds, somewhere in that general range. And your solution has to solve any possible test input within that time limit. So and the test cases can be quite large. For many of the problems, it's possible that the input could involve, say, an array of hundreds of thousands of elements. And so a key consideration when coming up with solutions is devising an algorithm that's not just correct, but also efficient. For some problems, you might need, or it might take big O of n solution to pass. For some problems, big O of n squared. But generally, problems with solutions that have the wrong time complexity are unlikely to get accepted. You can see the scoreboard here. Still, University of Montreal continuing to attempt problem H, but no luck. We've also seen 1 attempt so far on problem C and a pending submission from NYU Team 2 on problem E. I think they got right answer on that a moment ago, so we'll see how they do now. Carnegie Mellon now is is ranked first after solving D as their 5th problem. They now have a 9 penalty minute lead. Congratulations to them. We have Michigan now on 5 problems. So so now the list of teams on 5 problems is growing, and so now there's some pressure on Michigan State to debug their solution to B in order to move back into the top ranks. Oh, and Michigan State ended up switching to problem D. They got that accepted. Now they're in first place with a 16 penalty minute lead. Of course, because their penalty on B could potentially hurt them once they solve that problem. But for now, they remain in a pretty strong position. The other advantage they have is they have a draft of a solution for B. A common strategy that teams will use is they have access to a printer, so they will print out their solution to one problem that ends up, or when that solution is wrong, while someone else takes the computer to solve a different problem. So it's possible that they might even like already have an idea for how to debug their B, just because the team member who thought about that problem originally could have like figured out what the issue was while someone else typed D. This is like part of the strategic consideration that comes up from the contest rules, which specify that even though each team has 3 members, teams can only use one computer, and so a big part of doing well in this contest is figuring out how to use each team member's time efficiently, even when they don't have access to a computer. MIT is now attempting K. This could be the 7th problem to be solved, and it would make them the first team to get to 6 problems. Let's see how they do. They got wrong answer, so no luck, but we'll see if they can figure out their bug, or if K is a harder problem than they think. So let's scroll down a little and we can see how things are going elsewhere on the scoreboard. So about 16 teams on 4 problems. And looks like around 50 to 60 teams on 3. So still lots of teams doing well, but things are slowing down a little bit as some of the teams start to struggle a little bit more with the medium difficulty problems in this set. UMass Amherst, let's see, penalty on I. So no luck getting to 4 problems for them, but hopefully should be able to get that debugged before too long. Still more teams getting to 3 problems. Princeton attempting I as their 5th problem. We'll see whether that ends up being right. University of Toronto attempting H as their 5th problem. And University of Toronto got accepted, so they're now in 8th place, and we have the first solve on problem H. So congratulations to them. Or MIT let me register, attempting B as their next problem. Still waiting on Michigan State to try to resubmit their B, so, as well as MIT attempting K again. We'll see who can debug that first. MIT let me register now in ninth after solving problem B. So they're now behind their MIT Monkey is typing by just 18 penalty minutes. So pretty close race so far between the two teams from MIT. But again, if Monkey is typing can solve K quickly, then they could potentially take the lead that way. The Princeton has a solution in progress for I. They are the top, or they're still the top team on 4 problems. Again, not sure how up to date the results are for the Greater New York team, so possible that they actually got that right a little while ago. We'll just have to see in a few minutes. Yeah, I think we should review or view the current results for the Greater New York teams as tentative. I think their judging is a fair amount behind. Receive word from the team that they are actively investigating the issue. Hopefully, should be resolved before too much longer. So for now, we have up to date results for the East Central and Northeast teams. We'll see how the Greater New York teams are doing once their judging systems are back in a good state. NJIT attempting to become the first team to solve E. MIT resubmitting their solution to K. See how both of those go. MIT takes another wrong answer on K. NJIT still running on problem E. Let's see how they do. McGill attempted C, which I believe has not been solved, but got runtime error. NJIT still running on E, but they're in Greater New York, so I guess we might not know for a while. All right, well, potentially some teams might start solving E soon. Would be a bit of an unusual strategy to go for E as the second problem, but we'll see how things go. Now the second team from MIT attempting K. Sort of interesting that the two teams going for K, both from the same school. Seems like K is a tricky problem to get right, so we'll see if they can get it. Should put them in a good position, but unfortunately they get wrong answer. Grove City College also gets runtime error on K, so seems like that might be a tricky one to get right. MIT now switching gears, finally going for problem D. Every other team in the top 25 has it. Get wrong answer, unfortunately. Do think D is a straightforward enough problem they should be able to figure out the idea before too much longer. And Carnegie Mellon now has solved I. They're the first team to solve 6 problems. They've gotten there in sort of the expected way by solving all 6 of the easier problems that have most of the solves so far. Congratulations to them. Also worth noting that it is impossible for any team to pass them on 6 problems. Michigan State, if they saw would increase their penalty by 80 minutes if they. Sorry, it's not exactly true. If Michigan solved a problem other than B right now, their penalty time would become about 165, which would put them in the lead. If they solved B, it would become 185, and any other team would have a penalty time over 181 if they solved another problem right away. So Carnegie Mellon looks to be in first for the immediate future. But of course, they still lots of problems to solve, so they'll have to keep working in order to stay there throughout the contest. University of Michigan gets accepted on prom B, so getting more solved on B. Congratulations to them. And MIT Let Me Register passes MIT Monkeyist typing. They become the first team to solve problem K. Now have a penalty time of 238 minutes and can still attempt the somewhat easier problem I. So there's a significant chance that this team could become the first to solve 7 problems, which put them in the lead. Waterloo Black now attempting B. This would make them the next team to solve 6 problems. It would put them into into second place, and they get it right. Congratulations to them. Be interesting to see. I do think that we're getting the submission log we see from Greater New York is up to date. So Princeton resubmitted their I, so possible that they found an error or that they did get accepted, but the results aren't pushing to us. Michigan State resubmitting B. This could potentially put them into second place just by a few minutes if I'm doing my math right. Let's see if they get it right. And they do. So yeah, second place, just 8 minutes outside of first. So now they have solved a set of 6 easy problems. H and K do have one more solved, but it does seem like things might slow down a little bit from here as the teams have to work on problems that are a little more difficult than what they've encountered so far. see now 27 teams have at least 4 submissions. We are seeing we are seeing a little bit more variety in the set of problems being solved and in the solve counts. Couple of teams on 6, couple on 5, larger number on 4. About 70 teams on 3. Expect that many of the teams are still going to be working throughout the contest to get to the our solutions for the 3 more straightforward problems. Even those are pretty tricky, and it's a testament to the strength of the top few teams that they're able to get accepted on them so quickly. Great. So now, yeah, again, just to recap where we are, we have 4 teams on 6 problems. Still a couple of other teams trying to get there. A few teams on 5 problems. We're going to take a break for a couple of minutes, and then when we come back, we'll start discussing some of the contest problems. Talk through the solutions or the tricky parts. Think about like how teams are doing, which or the relative difficulty of the problems, that sort of thing. So stay tuned, and we'll be back in a couple minutes. Right, we are back. Cool. So, while I was gone just a moment ago, team MIT Let Me Register became the first to solve 7 problems, somewhat behind on penalty time, but still in a pretty good state. 2 problems ahead of the other team from MIT. So, that puts them in a pretty commanding position to do well in the rest of this contest. Also, the other thing to note is that none of the teams on 6 problems. Sorry, that's not true. Only one of the teams on 6 problems has solved any problem other than A, B, D, F, G, or I. And so that gives them an advantage just being ahead on the trickier problems. To talk a little about the set, I think that having looked through the problems a little bit during the break. University of Toronto, by the way, attempting I, that could take them to 6 problems, and they still have G left to solve. Looking at the set for a bit, I agree with the teams that the easy problems are A, D, F, and I and G. I actually would have thought that I is slightly easier than G, but there is a bit of a trick in the problem statement, and it's easier to get wrong than G is. So it does seem like teams are having a little bit more of a success with G. Afterwards, the teams are having some success with problem B. I expect that by the end of the contest, H will do some amount of catching up. I think H is slightly harder than B, probably easier than K, which some of the teams have been going for. And then just to look at the statistics so far, there's still the one attempt on C has had a couple of failed attempts. E has had some failed attempts. No one has attempted J or L, and then K has been solved by MIT, attempted by several other teams. I do think that there's some potential for the stronger teams to do pretty well on E and J. I think J in particular has an intimidating problem statement, but should be pretty doable for the top few teams, and so we'll see when they get to it. But once you read and understand the statement, I think that problem J only requires relatively standard techniques, and I would expect that the top teams will get it without struggling too much. L and C are both geometric problems, and I think they are a little bit on the harder end, both as a function of just being geometry, and because and in general they're relatively challenging problems compared to the rest of the set. So we'll see. McGill just attempted C but got time limit. If I had to guess right now, I would expect C to be the last problem from this set to be solved, but we'll have to see how things go. Obviously, anything can happen. Cool. So I think we're now going to, if I can get my windows to show up the way I want them to, gonna go over a couple of the problems. Still be able to see the Q on the side, so hopefully, any scoreboard updates we should be able to stay aware of. Give me just 1 second to get this into a good layout. Cool. So yeah, we're now looking at one of the problem statements. This is problem D. This is teams. Sorry. Before I do that, Waterloo just became the first team to solve E. Congratulations to them. Right after I said thought J and E are some underappreciated problems in this set. Also interesting. Also somewhat interesting that MIT has yet to resubmit their D or their K. I feel like if I was them, I would be pretty intent on solving D, just given the large amount of problems. 13 from MIT. MIT Let Me Submit has just became the first team to solve C, so quickly proving me wrong. I have to say it's a pretty straightforward solution. It is true that they've spent a good amount of time on that without solving the other problems, but Likely that C is not one of the easiest problems in this set, but yeah, we will see how the other teams feel about it from here. Anyway, to talk about D for a moment, just to give an illustration of what one of the simpler problems in this set would look like. So this problem centers around a ranked choice election, where all the voters are marking their ballots in order of preference, and at the start of each round, we count up all of the first choice votes, and if a candidate has more than 50% of the first choice votes, that candidate wins. Otherwise, the candidate with the fewest least place votes is removed from the ballots, and all the remaining candidates who those voters rank second move up. So if a candidate ranked A, B, C, D, and then A is eliminated, their vote transfers to B. If B then gets eliminated, their vote transfers to C, and so on. And then after this, we return to the next round, and this just keeps going until the candidate with the majority of the votes wins. Okay, so we have a candidate who is in second place on the first ballot, and we wanted to figure out the minimum number of rounds after the first that it will take to obtain a majority of votes, assuming or given that we're in second place after round 1. And so we're given the number of candidates, the number of first place votes each candidate received, and then we have to output either impossible to win if there's no way for the second place candidate to take the lead, or the number of rounds after the first round that it will take to win, if everything goes perfectly for the second place candidate. So the trick here is that we can use a sort of greedy strategy, where in this first example, for example, it's impossible to win because in the first round the candidate with 1 vote gets eliminated. Even if which we're in second place, so we know we have 67 votes right now, even if we get that vote, we still lose to the candidate with 70 votes. Looking at this second example, though, we have 69 votes, and so in the first round, the candidate with 1 vote is going to get eliminated, and the insight is the ambiguity here comes from we don't know who their votes are going to be reassigned to, but of course the best case scenario is for those votes to go to us, so because our goal is to get to over 50% as quickly as possible. And so we get that 1 vote. We get 2 votes, but then we still don't have enough to win. And then in the second round, the candidate with 2 votes gets eliminated. We can take both of those votes for ourselves, bring us to 72 votes. That's still not half of all the votes, but then in the third round, the candidate with 12 votes gets eliminated. We are now up to 84 votes, and that is more than half. The other candidates now have 70 and 13, so they have 83 votes. We have 84, so that's enough for us to win after 3 rounds. MIT, by the way, resubmitting D. Cornell now in 8th place, and after quickly solving 2 problems in short succession. I'll show the scoreboard again real quick, just because it looks like we now have up-to-date information on the teams from the Greater New York region. So let's pull this up. So you can see still the East Central and Northeast teams are in really strong position. MIT let me register has attempted H, gotten wrong answer, but they could very well be close to getting 8 problems, which would put them in a very strong position. This is a pretty strong team. They have at least one, maybe several, several. I think at least one of their team members is a Code Forces Grandmaster, and 2 of them have qualified for the USACO camp, putting them in the top 20 or so high school competitive programmers in the U.S. back before they attended MIT. So a strong team, I think, would be a pretty impressive upset if they managed to defeat the MIT team currently in 9th place. So we'll have to see how the rest of the contest goes, but best of luck to both teams. Other than that, I believe Cornell is now in first for the Greater New York region, followed by Princeton and Columbia. Cornell on 6 problems, Princeton on 5 problems, and Columbia on 5 with the worst penalty time. We'll see how the rest of the contest goes, the Columbia team, the Greater New York teams might be at a slight disadvantage, just having more delayed feedback from the judges, and so it's possible that they'll be able to get through the problems at a faster pace over the rest of the contest. Carnegie Mellon, meanwhile, attempting K, and they get it right, which puts them into first place by 40 penalty minutes. Again, like, I think if you're the MIT Let Me Register team, you really care more about how the other MIT teams are doing, since at this point, the both MIT teams are well within NAC qualification range, and it looks like the greater challenge will be to become the winner from among the MIT teams. So in some sense, it's not as scary that Carnegie Mellon is now in first overall. But of course, there's some glory associated with being first in the overall contest. So surely, I'm sure MIT will want to solve H before too long and take first place back. Cool. Yeah. So going back to problem D. So yeah. So the only real decision we have to make in this process is whose votes do the eliminated candidates' votes go? Or sorry, which contestant do the eliminated candidates' votes go to? And if we greedily choose to move all of them to ourselves, we can just simulate this process, figure out how long it takes for us to reach first place. One slightly tricky thing is if you're trying to add up the total number of votes in the election in order to check whether or in order to figure out how many votes are necessary to win. Well, there are 20 candidates and each can have up to 10 to the 9th votes, which means that the total number of votes can be up to 2 times 10 to the 10, which is too large to fit in a long variable in C++. So, and so that makes things a little bit tricky. Means that if you use an int rather than a long, you could potentially take a wrong answer penalty. I'm guessing that's where some of these teams are getting WA. In any case, we'll see how, or we will see how things go, and hopefully the remaining team still working on D will be able to solve it without too much more difficulty. Somewhat interesting that the two teams that are having some difficulty with problem D in the top 25 are both from MIT. So it seems like likely a coincidence, but somewhat interesting that those just happen to be the two teams having trouble with the same problem. Michigan, by the way, is attempting problem K. We'll see if they get it right. It's not up to me, and they do. They move into second place. It actually is not obvious to me. If I was ranking the relative difficulties of these problems, I actually do not think that K is the 7th easiest problem in this set. So I think this might be some amount of a scoreboard effect where teams see that everyone else is attempting K. But I'll be curious to see if other teams can take the lead by getting any of. I think that H and J, I feel fairly confident, are easier. Possible that C is easier given that MIT Let Me Submit team solved it already, although hard to say because I personally think C is one of the trickier problems in this set. But anyway, so there is some room for teams to improve their penalty time and catch up faster by solving problems in a different order. Toronto, by the way, just got to 6 problems. Still a little bit slower on penalty time than Toronto B. But they do have the advantage. They being Toronto A. Toronto A and Toronto B have solved the same set of problems. Toronto B slightly faster, aided by their first to solve on problem I. So should be pretty close to see which of those two teams comes out on top and has the chance to represent the university at NAC. MIT Let Me Register now reattempting H but quickly gets wrong answer. Waterloo White attempting K. Okay, so as all this is happening, we'll maybe talk about one more problem. Let's see which one would be interesting. Let's do problem we'll do problem G real quick and then talk about I in a few minutes. So problem G is we have a bag that contains R red balls and G green balls. We're going to draw 2 balls at random, and the probability of getting one ball of each color is 2rg over r plus g minus 1. Just a relatively straightforward formula. Our job is to write a program that takes as input a rational number p over q, and we have to determine whether there's a number r that's at most 10 to the 6th and a g greater than or equal to r, for which p of r comma g is equal to p over q. There are probably multiple ways you can approach this problem, but I think one thing you can do is just write, and let me see if I can to log in, do that in a bit, to write notes. But I think one thing you can do is just set this expression, since r is less than or equal to 10 to the 6, a solution that iterates over each value of r and checks if a corresponding g exists will be fast enough. So what we can do is we can take r, we can and then we can cross multiply, getting the equation g over, or 2rg over r plus g minus 1 equals p over q. P over q, of course, are given to us in the input. And we can cross multiply, and what we get out of that is a quadratic equation in g. And so the teams can then simplify that and then check if a solution exists and is an integer by using the quadratic formula. And if so, then that gives you a value of g. And so you can since it's okay to iterate over every value of r, we can just do that until we found a working value of g, or until we've checked every r. One thing to note is that we have to iterate over the values of r in increasing order, since if there are multiple solutions, we are asked to output the one with the smallest r. So this, and again, I think we did see earlier that this is a problem that some of the strong teams were solving before D early, and I think that does make sense just because the problem statement is so quick and the implementation is relatively straightforward that if you're a really strong team, you're probably going to quickly see this, realize that it's doable, and then do that before you spend a bunch of time reading a problem like D that has a pretty long string of text. That's where we are for now. We'll come back later and think through some of the other problems. We're now right about a third of the way into the contest. With some teams already on 7 problems, it does seem like there's a good chance that at least one team will be able to solve every problem in the set, but very much unclear, especially with several problems still unsolved. I think J and L both have no solutions yet. So we'll see if those end up being particularly tricky for the teams, or if just time pressure makes it hard to get all 12 problems within the span of 5 hours. But so far, some teams look like they're in pretty good position to take a crack at it, at least. Bia gets to 6 problems by solving B. Congratulations to them. Over in the open division, where contestants who are not competing officially can attempt to solve the problems for fun. Kevin Sun, K-Sun48, one of the top contestants on Code Forces, has solved 9 of the problems so far with a penalty time of 360. So pretty impressive performance, and has yet to solve C, J, and L. So suggesting that those might end up being the most difficult problems in the set. I know, we'll see. I think if I'm not misreading J, I think it might be overrated. There might be a scoreboard effect here, but we'll have to see. Waterloo, meanwhile, has solved problem K, did it on their first try, so congratulations to them. Now they're just over 20 penalty minutes away from the lead. So if Waterloo hadn't gotten that penalty on problem D, they would be only a minute behind. Harvard Waffles attempting K as their sixth problem. But no such luck. They're in a bit of a tricky situation, Harvard, because they have penalties on both I and K. So likely they're alternating between debugging those two problems, and will have a hard time moving much further until they get accepted on at least one of them. Or I think they figured out their bug in K. They're resubmitting very quickly. Taking some time to judge, so they looks like they might have a chance. And they get it right. They get AC. 3 penalty submissions, but it does move them up in the rankings quite a bit, all the way to 11th. They are now within the NAC qualification range. MIT now attempting E. MIT Monkey is typing attempted E, got wrong answer, so now has incorrect submissions to 3 problems. Which again, as I was just describing for Harvard, it's a pretty rough situation for them, especially when they are already now 2 problems behind MIT Let Me Register. But Let Me Register is getting held up by problem H, so we will we will have to see how things go for them from here. And I think I do actually see what is potentially an easier way to solve C. So I think that makes me think L is probably the hardest problem in this contest, and then D actually is reasonably doable. And I think if a team thinks to try it soon, it could be faster to implement than some of these other problems. So could potentially be some edge in realizing that C is somewhat doable before too long. But I know for what it's worth, just like having read the problems. Oh, and hold on, MIT is attempting H again. Let's see how they do, and they get it. So they are now on 8 problems with a 3 problem lead over Monkey is typing. Penalty time is a little bit tricky, but if Monkey is typing were to get their 3 problems that they have attempted right now, they have 2 penalty submissions each. Their penalty time would come out to 519. So it is a pretty solid lead. I think if you're Let Me Register, you are probably thinking like you want to get those last 4 problems as quickly as possible, since it is possible for the other MIT team to catch up on problems, and you don't want to get into a situation where you have a very impressive penalty time, but you end up behind the other team from your school just on problems solved. Princeton just moved up to 6 by solving problem B. They are not the first team in Greater New York to do so, but they do have a significantly better penalty time than Columbia 1. Also worth noting, Columbia 1 and Columbia 0 are the top two teams from the second and third place teams in Greater New York. So only one of them can qualify. Right now, that means Cornell, under the current state of the scoreboard, would be guaranteed an NAC slot. So it's going to be a little bit tricky to see which of for the two Columbia teams to beat out the other team from the same school in order to make it to NAC. MIT let me submit, attempting problem B. This would make them the second place team from MIT. And they get it right, so they are now in 10th place. Again, top 3 for Northeast, but still not within NAC qualification because of the one team per school rule. Yeah, all 3 MIT teams are pretty strong. To recap, we have MIT Let Me Register, which has 2 USACO Camp qualifiers and at least one, maybe more Code Forces Grandmasters. We have the we have MIT Let Me Submit, which has multiple IOI gold medals and a Code Forces Legendary Grandmaster and 2 International Grandmasters. And then the MIT Monkeyist typing team has, I believe, 2 IOI winners and an IMO perfect score. So lots of really strong contestants. Waterloo Black, by the way, just moved into first place by solving problem H. Now on a better penalty time than MIT Let Me Register. Waterloo Black actually, I believe, has a contestant who is, if I'm recalling correctly, been to the World Finals representing the Colorado School of Mines in the past. So, it looks like so far a pretty good debut for them in the East Division here. Yeah, so now looks like as the problems get trickier, lots of differentiation among the top teams just on the number of problems solved, with 2 teams on 8, 2 teams on 7, and then another 10-ish on 6, and then plenty more on 5. Still lots of room to catch up though. Again, no matter how slow you are to get to a certain number of problems, solving more problems always wins. And so any team at this point can still catch up just by solving lots of problems quickly. Here now, a total of 31 teams have solved 5 problems, which is pretty impressive for less than 2 hours into the contest. Plenty more with 4. Looks like interestingly, a lot of these teams are actually converging on B as the fourth easiest problem instead of G or I. Still, G may be the most popular, followed by B and then I. And I do think B is somewhat solvable using standard techniques, and I think it's fairly transparent that you can use relatively well-known algorithms to solve it, rather than G and I, where I feel for G, you can get caught up in edge cases solving the quadratic, edge case or overflow, or double precision errors if you choose not to solve it by working entirely with integers. And I think if you don't read the problem carefully, you can get tripped up on. So it does make some sense that for some of these teams, it's a bit easier to get accepted on B. Let's talk about maybe just for completion, we can talk about the other two easy problems now. The problem real quick. So this is problem A. This is the judges and the team seem to agree that this is the easiest problem in this set. So we have some number of small, medium, and large pizzas. Each box still has some slices remaining. And so we can combine the leftover slices from the same size of pizzas into a box of the right size, but we can't put, say, a slice of a small pizza into a medium pizza box, and we can't put more slices into a box than it originally held. And so we have to figure out how many boxes we'll need to hold all the leftovers. And so we're given the number of pizzas that were ordered, we're given whether the original size of each pizza and the number of leftover slices, and we have to output the fewest number of boxes that we need. And so the trick here is we just need to add up all of the number of slices, or all the numbers of slices for each pizza size. So in this, third sample input, we have 1 small slice, 4 medium slices, and 1 large slice. And then just using some basic arithmetic, we can figure out how many boxes do we need for the small pizzas. If each box can hold 6 slices, how many boxes do we need for the medium pizzas if each box can hold 8 slices, and so on. Carnegie Mellon, by the way, attempting to problem H, they'd be the third team to get 8 problems, but because of their penalty time, might be able to move up into first or second, and they get it right, and their penalty is strong enough for them to be in first place now. So congratulations to them. East Central looking very competitive with Carnegie Mellon, between Carnegie Mellon and Waterloo. Anyway, so the other remaining easy problem on this contest, insofar as any of the problems are easy, they're all relatively tricky, is problem F. So essentially we have this sequence of rational numbers where S is composed of an infinite number of blocks, where each block contains the a list of fractions starting with with I, the number of the block, and then going up by 1 over I until you reach the next whole number. So for example, a block might be 4, 4 1/4, 4 1/2, 4 3/4, and then 5 starts the next block. MIT Monkey is typing, by the way, did manage to get accepted on E, so that's their and so they do still have D and K incorrect submissions, but could move them higher if they can debug them. But for now, good for them now that they only have 2 problems to debug rather than 3. They could catch up quite quickly if they can figure out what's going wrong with their attempts at D and K. Harvard attempted H to try to get to 7 problems, but with no luck. Okay, so anyway, so for problem F, we have to take in an integer n and then output S of n. And so I think a good thing, or what we really want to figure out here, is which of these blocks is n going to actually, is n going to actually fall in, and then what's its position within that block. And so and it turns out we can just do this using brute force by saying okay, there's 1 element in the first block, is n equal to 1? If not, then subtract 1. Then 2 elements in the second block. If n is at most 2, then we know it's in that block and we know what its position is. Otherwise, subtract 2. Now there are 3 elements in the third block. If n is at most, at most 3, then we know it's in the third block. Otherwise, subtract 3, and so on. And the idea is that, you might ask okay, well, is this going to be fast enough? N can be up to 4 billion, so something that runs in big O of n won't be fast enough to get accepted. But for this problem, a helpful fact here is that the sum of the first k positive integers, which is the total length of the first k blocks here, is big O of k squared. And so that means that if n is an element of the kth block, then n is O of k squared, or k is O of square root n. So we only have to go through up to like square root of n blocks before reaching the block that contains n. And then from n, so that means that this will take like O of square root of n time, which even for n as large as 4 billion will be comfortably fast enough to pass in time without difficulty. MIT let me submit, by the way, trying to solve K. If they get it right, they would be now the second place team from MIT. I think they have at least one penalty, but this time they get it right. They're in 5th place overall on 7 problems. I think they are. Let me check this real quick. Yeah, so they still, because their penalty is a little bit worse. So first of all, they got K on the first try, so well done to them. Their penalty is slow enough that even if they got an 8th problem right now, they would still be behind MIT Let Me Register, but does put them in a better position to make the comeback. And both Let Me Submit and Monkey is Typing still have a D left to solve, so there's some potential for hopefully them to like find a relatively small, easy bug and then move up onto and then in the case of Let Me Submit, move up onto 8 problems. Okay, yeah, so continuing with problem F, the one thing left to deal with is the output format, because rather than just like outputting the number as a decimal, which is easy to do with a double format, we have to output a single integer if the answer is a whole number, or the integer part and then a proper fraction that representing the fractional part of the number. Sort of like the same format that you see up in this row. So that makes things a little bit more annoying, but you roughly need to just like check if we're in the first element of a block, and then if so, then make sure to output the integer. Don't output like 26 and 0 over 1. And then secondly, we have to make sure that if there's a fractional component, it's in lowest terms. So we want to output like 4½ instead of 4 2/4. And so we can do this just by either like implementing the Euclidean algorithm on our own to calculate GCDs, or by using a built-in GCD function in our programming language. So hopefully, like teams that are familiar with their standard libraries shouldn't find this too difficult to do. Cool. Let's go back to the scoreboard for a bit, and then in a few more minutes we will talk about more of these problems. Again, I'm hoping to cover all 12 of them by the end of the contest. I think we'll have enough time to do that. Yeah, so looking at the top of the board, 3 teams on 8 problems, 2 teams on 7. So all of those teams are in pretty solid positions right now. Again, though, the top 4 teams are all within the qualification slots. MIT Let Me Submit, not quite there just because they are behind the top MIT team. We can talk now about where the NAC qualification bars are for each individual group. So to start, let's look at East Central. For East Central, we have Carnegie Mellon, University of Waterloo, and University of Michigan are the top 3. They're all in good position. Michigan State is after a strong start, has had a little bit of a hard time getting to 7 problems, so we'll see if they can get there. Still in a very respectable 6th place. 6 out of the top 10 teams come from the East Central Regional, so definitely a strong showing by them. University of Toronto actually making their 3rd attempt at problem K, and then Waterloo Gold finally making their 1st attempt at D, which is a little bit surprising this late into the contest. Waterloo does get D on their 1st try. Congratulations to them. And then and Toronto gets K. That moves them up into 6th place above Michigan State. Getting to 7 problems is just worth a whole lot, even if your penalty time is a little bit slower. So this is what we have for East Central. For Northeast North America, the MIT teams round out the top 3. But the automatic NEC slots right now are going to MIT Let Me Register, and then Boston University and Brown. Monkey is Typing actually is making their 3rd submission on K, and they get it, which moves them into 6th place, just behind Let Me Submit on penalty time, and then behind Let Me Register on problem count. So Let Me Register still in a good position, but again, both of these two MIT teams have the like relatively straightforward problem D that they can hopefully like figure out quickly and get you 8 problems. And from there, it's really anyone's game to finish the rest of the set. So hopefully for Let Me Register's sake, hopefully they have made some good progress on a 9th problem. C and E have both been solved, so they could go for either of those. Oh, and actually now Let Me Register has been going for J. Good choice by them. I've been saying that someone should try and solve J. Let's see if they get it right. So it's taking some time to judge. I think J also, there's some risk of time limit exceeded. I think J, the time limit on J may end up being a little bit tight if your solution isn't optimized well. But they get a C. Congratulations. They're the first to solve problem J, first team to get to 9 problems, and now have a 2 problem lead over the other MIT teams and the rest of the Northeast region. Okay, so anyway, so MIT, Boston University, and Brown currently in the NEC slots. Harvard only 6 penalty minutes behind. We'll see if they can catch up. University of Toronto B, by the way, we'll go back to the overall scoreboard for a moment. They're attempting H, but wrong answer, so couldn't quite get to 7. Think that if Toronto B got a 7th problem right away, they would have a fairly substantial penalty lead over Toronto A. So again, very close competition between these two teams. Okay, so now looking at Greater New York. Top 3 teams are Princeton and then the 2 teams from Columbia, which means Princeton, Columbia, and Yale currently occupy the NEC slots. The 2 Columbia teams separated by only 36 penalty minutes, meaning that it really is anyone's game to see which of them qualifies for NEC. Columbia 2 even is only 1 problem behind, so they're very much still in it. Now looking at where this leaves us overall, I think there are very likely to be some wildcard slots. I believe last year there might have been 8 wildcards to the NEC from the East Division. So even though Toronto is not currently in the NEC qualification bounds, for example, I think they're relatively safe to get a wild card. Michigan State in good standing to get a wild card. Purdue Fearless has now taken a solid lead over the other Purdue teams, and they're in pretty good, or they have a pretty good shot at a wild card. Actually, sorry, Purdue Fearless only a 20-minute lead over Frosted Entropy. But whichever of those teams finishes in first, reasonably likely to get a wild card. And now just as I say that, Purdue moves into 5th place over the bottom 2 MIT teams by solving problem K. So now they still, because of how strong the East Central region is, still would need a wild card to advance, but seems pretty likely that if they maintain their position, they will get one. Outside of that, other teams in contention for wild cards. Harvard has a shot down in 23rd. Lots of duplicate schools above them, giving them a reasonable chance. Cornell in contention, NYU in contention. All depends on how the rest of the contest goes and how many slots there are. Princeton attempting K. This is their first submission, but they get wrong answer, so no luck there. Looking at the statistics to see where things are now, lots of solved on K now. In fact, Brown University Team 3 just got K as their 4th problem, which is pretty impressive to solve K before solving all the other problems that the teams at least seem to find a little bit easier. Looks like roughly the state of the board is pretty similar. It looks like A is the easiest problem, with A, D, and F forming the easy end of the set. B, G, and I now are all form in the medium end, and then all of C, E, H, J, and K have some solves. I think it is actually harder than you would think to decide which of these is easier, or is the easiest, just because teams started solving K first, and so like naturally that leads more teams to attempt K. And so even if K isn't necessarily the easiest of these problems, it has more solves, just as a function of teams having been quick to attempt it. But H also up there, though lots of people getting penalties on that too. And then C, E, and J have some solves. I'll be interested to see if J ends up getting more attempts now that it's been gotten accepted. Some people know that it isn't the extremely hard problem they might have thought it was. All just remains to be seen. L, meanwhile, hasn't even been attempted yet, much less solved. So that seems likely to end up being the hardest problem in the set. But we'll just have to see how things go. Possible that C or J ends up being up there, but it does seem likely that L will end up well on the harder end here. Okay, we're going to take a break for a couple of minutes, and then once we're back, we will check on the state of the scoreboard, possibly discuss one or two more problems, and see how the rest of the contest unfolds. See you in a few minutes. All right, welcome back. So far, no huge changes in the board since the since I left. I think the most significant change is the MIT monkey is typing now on 8 problems with the same penalty time as let me register. Of course, going to be worse by at least 140 minutes once they get that next problem accepted. And so, yeah, things are tightening a little. Again, both MIT teams have the potential to solve D. MIT Monkey is typing already has C accepted. They could even potentially go for H or J next. So I do think this one is likely to come back down to penalty time. We still don't have a sense of how hard L is for the teams. But it could very much be a race to solve the entire set with as small penalty time as possible. Aside from the MIT Civil War, we have 4 teams with at least 8 problems, and then another 8 with 7, plenty more with 6. With the way the contest is going right now, I'm guessing that teams will need 9 problems, maybe 8, but I would guess 9 to qualify for the NAC at the end of the contest. But we'll see how much further each of the teams can get, and then we'll let the scoreboard scroll a little to see how the things are going for the rest of the competitors. Waterloo Red going for K would bring them to 8 problems if they got it right. And they do, so they're in 4th place now. Congratulations to them. Waterloo Gold also just got K to get to 7 problems. looking at the solve statistics, we are still waiting for more submissions on J. C and E, it looks like teams are now coming around to the idea that they might be comparable to H in difficulty. Three solves on C, 4 solves on E. I expect a lot of these to catch up to K over time, but we'll have to see how things go. Maybe K is a little bit easier than this set, but just remains to be seen. Okay, why don't we talk about another problem? Let's see. So we've gone over A, D, F, and G so far. So I seems like the logical next one to do. So just a moment, and we'll pull that up. Cool. So for problem I, we have a number period game. Or sorry, number pyramid game. We're trying to find, or we have like some cards that each card contains a pyramid of squares, some filled with numbers and some empty. The goal is to put values in each of the empty squares such that the sum of the sum of the values in any two adjacent squares is the value of the square above them. So for example, in this sample case, the numbers that go here and here have to add to 18. The cards are also set up so that they can always be solved by doing sweeps through the card, where with each sweep we go from top to bottom and left to right, and if we can determine a value from its neighbors, then we fill it in. It might be possible, like using the fact that the final values in every square have to be less than 100 in absolute value, it might be possible to do some sort of like caseworky approach that finds a unique solution even when this is not the case. But if a unique solution can't be found like using this particular method, then we're calling the card ambiguous. Now we're doing as we do or make these cards, we found that some of the cards are either ambiguous or lead to contradictory values for one or more of the squares. And so we want to do a little bit of quality control, and so we're going to be given as input the number of rows on the card and then the values on the card, some of which, indicated by 100 in the input, could be empty. And then we have to figure out whether the card is solvable. If it's solvable, then we have to output the solution using a similar format to the input. If the card is ambiguous, then we have to say so. And if the card has a solution, but it has one or more values outside the given range, then we have to output no solution. Okay, so I think like the one like helpful note here is that we're guaranteed that we just want to check if a like card can be solved by or just by like doing passes through the card and filling in any value that's like uniquely determined by its neighbors. This makes things a little bit simpler for us because we can sort of do a breadth first search style approach, or even something less efficient because the input size is relatively small, where we sweep through the cards and just like again, as the statement suggests, determine everything or each number where, or like we can look at like each triangle of 3 cards. If two cards in a triangle are known, then the third one is uniquely determined. And then and we can keep doing that until we've identified everything or all of the like rows on the card. If this process like doesn't terminate, then the card has to be ambiguous. If it does terminate, then but we get a number that has absolute value at least 100, then the card is unsolvable. And then otherwise we can just output the solution. So we can sort of do a brute force style thing. One interesting question, which I'm still thinking about, is there ever a case where a unique solution can be found, but we can't do the but we can't solve the card using the like sort of sweeping approach that this approach describes? And I think the answer here is yes. I think that it is possible. Yeah, I think like one way you can design a card, and here maybe I'll go look at the open division just so I can like type some things. This is problem I. Yeah, so one tricky case that you might imagine is if we have a pyramid that looks like this. Now, none of the numbers in here can be filled by just by looking at their neighbors. So which indicates that under the statement in the problem, this card is ambiguous. However, the middle number here is if it's positive, then this plus 99 will be, or at least 100, so that doesn't work. If it's negative, this plus negative 99 will be less than negative 100, so that doesn't work. So in fact, like this number has to be 0, and then now we can like fill in the top 99, negative 99, and then 0 here. So you can see like a card can be ambiguous even if a unique solution exists. And so the problem does get a good amount trickier if you allow for there to be allow for there to be multiple multiple solutions. One thing that I think I actually don't have a great sense of what you would do to solve it if ambiguous meant like there are two solutions in general. And I do think it's like a little bit confusing the way the problem is stated. In fact, actually maybe you should let the judges know about this. That like here, like if a unique solution can be found, or we say a card is ambiguous if a unique solution is found using this method. But here we say if the card has multiple solutions. I guess this is a case that, or no, yeah. So we say like output ambiguous if it has multiple solutions. Here there's a unique solution, but it can't be found using the given solution method. So I think given the problem statement that this card should be deemed as ambiguous. If it was not, if like this didn't count as ambiguous, I think the problem would be considerably more difficult, and I don't immediately know how you would solve it then. I think it likely is possible, but would be a little bit tricky. Like one thing you could do is like fix the if you like fix the like top number, then in any row, if you like know all the values in the row above it, and you know at least one value in that row, then you can like use the solution. Then you can use like brute force approach to fill in the rest of that row. And so the like only challenge comes, and so you could like do something like iterate over all values of the top element and then try to fill the grid in. The problem though is that if there could be like, as in this example, entire rows of blanks, and dealing with those seems a little bit tricky. Yeah, so it is not totally clear how to it's not super obvious how to handle that. I think you could do something like, I don't know, for each row, it might be true that, yeah, I think it maybe just gets pretty tricky if you don't have this guarantee. So I do think like one way that teams can potentially like not solve this problem is by like not reading this part of the statement and trying to do something more complicated. But since we're only trying to like use the approach of filling in two numbers if their neighbor is known, then we can use a pretty straightforward approach. I'm going to see real quick if clarifications have been issued on this. Okay. Yeah, well, so that's what's going on with problem I. Think hopefully like teams will read the full statement and should be able to figure out what's going on here, but can be a little bit tricky if not. I'm gonna write a quick message. MIT let me submit, by the way, just got to into 6th place by solving E, only 17 minutes behind Monkey is typing. Again, neither of them still yet to solve the. So I think the race for top MIT team is getting more and more competitive. Right, cool. I just wrote a quick message, pass that along to the judges, and hopefully if a clarification on this problem has not been issued yet, will be. Or possible that I'm misreading or misinterpreting something, but I do think that I know this is a little bit of a tricky corner case where the problem statement and the output format at least superficially appear to disagree. A couple of questions in the chat. As who are the team members of Monkey is typing? That would be so Richard Peng pointed out how you can check this for yourself, but the team members are apologies if I'm mispronouncing any of these, but Kong Yang Zhou, Jiangti Dai, and Cheng Jiang. The first two, I believe, are both IOI winners. I think that's right. Yeah, they won the IOI in 2022 and 2024, I believe, and then Cheng Jiang won the or got a 42 on the IMO at some point in the last few years. Also a question, what solution complexity do you have in mind for problem J O of n squared? Yeah, I think I have an O of n squared solution to problem J in mind. The time limit, what is the time limit actually? Let me see if it'll let me pull this up. Time limit on problem J is 5 seconds, and n is up to 10,000. And the solution I have in mind is like, or it takes like n over 2 choose 2 times, so like really n squared, or so really like n squared over 8, I think. So I think it should pass in time pretty comfortably, but also possible that I'm getting something wrong. I mean, the teams do broadly seem to think J is one of the trickier problems in this set. Okay, anyway, so yeah, I do think, or so now we have gone over all of the 5 easier problems. I guess actually I now has fewer solves than B. Possible that like the teams that read the problem or that like understood the intended interpretation of the problem have gotten it, and then now most of the remaining teams have are getting like somewhat confused and don't realize you can just do the like straightforward brute force approach. I for what it's worth, like it wasn't obvious to me for the first while when I was looking at the problem. I thought you had to do something pretty smart, and we just saw a rare memory limit verdict on problem K from Indiana University of Pennsylvania. This means that the program took or consumed more memory than the problem statement permitted. This is pretty rare because except for a few problems, I don't think we have any of these on our set today that have where like the memory limit is intentionally shrunk to make like optimizing memory part of solving the problem. Or other than that, like typically you run into time limit issues before you run into memory limit. But I know hopefully they can figure out what's going on and debug that. Sometimes like things like, I don't know, repeatedly like adding more and more elements to a vector, say, can cause memory or limit related issues. I think University of Waterloo just solved, I think they just got problem E. They can check on that. Yeah, Waterloo Black just solved problem E, making them the second team on 9 problems. Just 2 minutes of penalty behind MIT. Looking elsewhere on the scoreboard, Carnegie Mellon could get you 8 problems and their penalty time would go up by about 170 now. So their penalty time, if they got you 8 problems, would be 557. So Carnegie Mellon could potentially take the lead just by solving 1 more problem. Otherwise, MIT let me register in a pretty good spot. And looking to go even further as they attempt problem E. Let's see how this goes. E has some potential. Both wrong answer and time have exceeded. They do get wrong answer this time, but we'll see if they're able to debug. Both other MIT teams have solved problem E. Let me register, of course, ahead on the basis of solving problems D and J. And so we'll see. Hopefully they can fix their E pretty soon, and that would get them on to 10 problems. her Harvard University waffles had been a little bit of a while since they got their 6th problem, and now going for a 7th on problem C, which is a bit of an unconventional choice, but we'll see how it works out for them. I do think it's not a crazy one. C has turned out to not be an insanely difficult problem, though of course harder than many of the 6 problems that they've solved so far. And Harvard ends up getting that one right, so they move up into now 17th place. So congratulations to them. Yeah, this was their the first problem that they've solved in just over an hour. So took them a little bit, but good that they but good that it all worked out for them in the end. Very exciting. Yale attempting to solve problem K to get to 7. Looks like Harvard is one of the teams that still has problem I left to solve. Harvard and Waterloo both have a substantial number of wrong submissions on problem I, so we'll see if they're able to get those dealt with. I would be curious to see. We're not able to see the team submissions, unfortunately. I'd be curious to see like what's causing the 2 MIT teams difficulty on D, what's causing the Waterloo and Harvard teams problems with I. But I don't know, hopefully those should all be resolved before too long, and they'll be able to get working on the hard end of this set. Also, it'll be interesting to see whether MIT is able to debug their E, or if they need to go back to the drawing board and notice an issue with their solution concept. Eastern University Bridge Spam, interesting team name, is attempting problem K. See if they can get AC. Give it just a moment, and they do on their get AC on their 3rd try, move up into 20th place. And we can see here, like, number one is the teams to have like mostly settled on K being the 7th easiest problem. I don't know, even seeing where the scoreboard is, I think I disagree with. Well, I don't know, it's not totally obvious. It's not a crazy problem to attempt, but I still am surprised that the teams haven't been having more success with H relative to K. It does seem like it's a like trickier problem than average to get right. You can see many of the teams have several wrong submissions on it, and for all the teams in the top 4, I mean, you can argue that it goes both ways. Like, partly they're in the top 4 because they avoided spending a lot of time debugging K, but partly they are like very strong teams that are good at getting problems right on the first try, and this led them to do well on problem K, which is then giving them an edge in the competition. We also just saw an attempt on H from Waterloo, which got wrong answer. So to wrap up the set of easy problems, let's go over problem B real quick. So I'll show you the problem. Cool. So for problem B, we have a decision process that existed, or that is formed by an and or tree. So each leaf just has a truth value, either true or false, and then each non-leaf vertex is either says and or. If it's an and vertex, then it takes in a bunch of inputs and returns the and of all of them, or vertices are defined similarly. And so as we do this, we're going to end up with some output from the root node. So in this example, like this and becomes true, so this or becomes true, this or becomes true, this or becomes true. So all 3 of these are true, so this and becomes true. So we want to change the output of the root node, and we have to figure out the minimum number of leaves that have to be changed in order to change the evaluation of the root node. Also, we're noting that the and ors are going to be structured such that nodes in odd levels of the tree are going to all be, or all be and or all be or. Nodes and even levels of the tree will be of the opposite type. Then we are okay, and so then we are like given a description of the tree. It's a bit of a non-standard format, which makes things a little trickier for some of the teams. Total number of vertices is going to be at most 10 to the power of 5. And we have to output the minimum number of leaves that need to be flipped in order to change the output of the root node. So I think there might be multiple things you can do here, but I think one thing that you can think about is a dynamic programming approach. So roughly like for each vertex of the tree, of which we know there are at most 10 to the 5th in total, we want to figure out how many flips we need to make in order to change the truth value of that vertex. And so we can sort of think, and so for obviously for a leaf node that's either true or false, we just need to do one flip to change its truth value. And then like going up, we can do a little bit of casework. If we have an AND vertex that currently evaluates to true, then in order to flip its truth value, we just need to change any of its underlying values to false. So we can like go through each of the each of its children and find the minimum cost to change any of them to false, just using our dynamic programming table. If it's an or if that currently evaluates to false, then to change its truth value, we need to change all of its underlying values to true. So we can look at all of the children that evaluate to false and compute the cost to change them to true. And then you can do a similar thing to OR, except like if it's an OR that evaluates to true, you need to turn all of the children to false. If it's an OR that evaluates to false, you just need to turn one of the children to true. And so that lets you like recursively compute this DP, and by iterating that from the bottom of the tree to the top, you can get the cost of changing the initial and. And so like here, this tree here corresponds to the first sample input. Here, if we just flip any one of these three values, for example, this and becomes false, and so this or becomes false, and so this and becomes false. An interesting thing is that this solution works in the slightly more general case where rather than like being guaranteed that the labels just alternate by level like and or. This approach like works fine if you can have if you can have like different this approach works if you can have different labels on the same level. It is however true that like if you have like an and then another like and is a child of it, then like you can sort of think about the like root the and that's that's the parent as like the and of like any of its children that contain or and like the children of any children that contain and so if there were two ands where one was a parent of the other, or two ors where one was a parent of the other, you could sort of like delete the and that's deep or that's the child, and then put all of its children as children of the parent, and then keep doing that until you get a tree like this. So anyway, the solution still works even if the input isn't given in this format, but any tree where like where the vertices have arbitrary labels, it could be like easily converted into a tree where the like labels alternate in the pattern given here. So it's like a bit of an interesting note about the structure of the problem. Anyway, but the overall implementation is relatively straightforward, and teams that are well versed in dynamic programming on trees should be able to get this relatively quickly. Indeed, like it looks like the contestants are collectively having a good amount of success on this problem. Going back to the scoreboard for a moment, no huge updates. Michigan State just got a wrong answer on problem H. And University of Michigan, no doubt trying to stay ahead of their competitors at Michigan State, now attempting problem H. Also wrong answer, so we'll see which of them gets it first. We do have an update from the judges where they're actively working on resolving the issue that we noticed in problem I. So hopefully a clarification should be pushed to the team soon. I think they're like, it is a little bit tricky because you can sort of interpret the problem statement in one of three ways. You can interpret it as like the problem as a problem statement is correct and a grid where there are like multiple solution or where there's a unique solution, but it can't be found just by like iteratively filling in anything that can be determined from two neighbors. Like if that's the case, it's ambiguous. You can interpret it the way the output format suggests, where if there's a unique solution, then even if it can't be found that way, you should still output solvable. Or you could like read the inputs or the like problem statement as like as asserting that the cards are guaranteed, or that like even after the errors possibly come in, the cards are guaranteed to be like solvable in this way. And so you could interpret it as like an additional constraint on the input where cards like the ones I came up with are not allowed. I don't think this is the right interpretation. The input section doesn't specify any such constraint, but always possible. That's what's going on. Waterloo Red, meanwhile, is attempting problem E. This would bring them up to 9 if they got it, but unfortunately they do not. Notably, even if they did get AC, they would still be well behind Waterloo Black on penalties, so in order to come back, they will likely need to get ahead on problems. And it is really coming down to the wire. It's now a little bit less clear that there will be many teams will solve the entire set. Like MIT has been on 9 for a good while. A lot of teams on 8. Like getting three more problems in the next 2 hours is a bit of a tall ask when you're looking at the hardest problems in the set. But yeah, I think a lot depends on how hard the teams find problem L. Cool. So let's see, how are we doing? Waterloo Gold has gotten accepted on problem H. Congratulations to them. And let's see. I think in a moment we'll probably talk about one of the other problems just to keep things exciting. But we will give it some time. Yeah. And Carnegie Mellon just got accepted on problem L. They're the first team to solve it. They're now on 9 problems. Congratulations to them. It puts them just barely into first place. Really tight competition between Carnegie Mellon and MIT. I think MIT was maybe marginally ahead, or no, sorry, it was pretty close before, and then Carnegie Mellon they lost a little bit of their lead getting to 9 problems, but got there in the end now, and now in a really solid position here. Now they just have C, E, and J left to go, and all of these have been solved. So now they know that there are no undoable problems left for them. Columbia, meanwhile, attempted to get to H or get to 8, but just got wrong answer on problem K. Looks like Columbia 0 still a problem ahead of Columbia 1, but with much worse penalty time, Columbia 1 could still get a 7th problem and move ahead of them. So within the Columbia 1 still has K left to do, which could be a good or a bad thing. If you think K is actually the next easiest problem in the set, then it means they have an easy way to get a 7th problem. But this remains to be seen. I do think that broadly the broadly, like the last 6 problems, I think that the like difficulty ordering is not is not that clear amongst them. Oh, MIT, by the way, now attempting problem B for the 5th time. Let's see if they can get accepted. They do not. No such luck today, but we'll see how. We'll see if they can figure out what's going on next time. Yeah, I do think like all of the, like among the last 6 problems, I think that I would say that no, it really is hard to tell. I would have thought that like E and L maybe were slightly on the harder end, but it really is not obvious like which ones are harder, and so we're seeing like a lot of different orders that the teams are choosing to attempt these in, and likewise, now I'm maybe a little bit. I think it is still pretty likely that the or that like 9 or maybe like a particularly fast 8 will end up being the NAC cutoff. But I think we're going to see a lot of different ways that the teams will get there. Forward scroll for a couple minutes. MIT, maybe they think they figured out the general gist of what's going on with B because they're submitting it again. But nope, 6 penalty on problem B for them. I'm curious. Maybe I'll pull up the problem again. I am curious if there's like any sort of ambiguity here that might. I do feel like when you're, it's unlikely that that such a strong team is going to be stuck on int versus long, which is the one issue that I can foresee on this problem for as long as they have been. And I do think like especially when you take this many penalties, it's a good strategy to just have someone else re-implement the problem from scratch. I would guess more likely there's like some sort of misreading or misinterpretation of the problem at play here. But unclear what exactly is going on. Chat asks, wait, is this geothermal? Yes, that is me. Pretty close competition. We'll see hopefully before too long who the first team to get to 10 problems is. MIT has seems like they might have a bit of a head start having already attempted E. Does seem like that's a problem that many of the top teams, like they've taken multiple tries but have eventually gotten it. Carnegie Mellon actually going for E now. Let's see if they can one-shot this problem. A bit of time, and they get it right first try. Carnegie Mellon with no wrong submissions so far, which is extremely impressive. The first team to get to 10 problems, maintaining their first place position will be pretty hard for anyone else to take away their lead now. Prior will need to get to 11 problems in order to do so, but of course they're going to be trying to get there first. For now, why don't we talk about another problem? We can maybe just moving in order of the number of teams who've solved each problem. We can do K next. Pull up the problem statement. Okay. So we're trying to like create a string that will specify which of each of 3 panels labeled A, B, and C are to be highlighted during each week of an exhibit, which may run as long as a year. So in other words, we're trying to like come up with a sequence of A's, B's, and C's with length W, which can be up to 52. And the issue is that not every like sequence of A's, B's, and C's is acceptable. There are a couple of rules we have to follow. Number 1 is that we can't use the same panel during 2 consecutive weeks except for the panel B. So B can be highlighted during 2 consecutive weeks, but not during 3 or more consecutive weeks. The second constraint is that no panel should be highlighted significantly more often than any other panel. So we have some integer D where D can be up to 10, and we have to ensure that any two of A, B, and C, or of like the like maximum number of any character and the minimum number of any character differ by at most D. That's our other constraint. And then the third constraint is that the sequence cannot be a palindrome. And so we're given the number of weeks in the exhibit, or in other words, the number of letters in our string and the value of D, and we have to output the total number of sequences that comply with these rules. Okay, so I think the like first tricky observation here is that if we think about doing some sort of dynamic programming, we can kind of encode like the state for our like variety and balance in a relatively straightforward way. Like for variety, we just need to keep track of like what's the last panel in A, was it a B, was it a C? If it was a B, have we seen like 2 consecutive Bs or just 1? That's like sort of an easy thing to encode in a like dynamic programming state. Balance too, like we can just keep track of how many of the A's, B's, and C's have occurred so far. Since W is at most 52, there are only like 52 cubed, or sorry, of like W cubed possible like balance states, and so that can be done pretty efficiently. And so if we only had the variety and balance requirements, then this would be pretty straightforward. We can just keep track of like how many A's, B's, and C's have we seen so far, what was the last character, or like what's the current state among the like options of like A, last was an A, last was a C, last was a B, and before that we had something different, so it's okay to put another B down, or like last was 2 B's. And then just like iterate over the choices of the next panel, and then like at the end, once we've used W panels in total, count the total number of ways where the differences are at most D. All that is fine. The issue is the palindrome constraint. That one's a little bit trickier because in order to encode like the constraint that like that the string can't be a palindrome, we would if we like were building a string from left to right, we would sort of need to know like the entire first half of the string to check if like the second half of the string is going to make it a palindrome. So instead, we can do complementary counting, where we count, okay, how many things how many strings satisfy the first 2 conditions, and then subtract out how many strings satisfy the first 2 conditions but not the third. So in other words, how many palindromes satisfy the first 2 conditions? And this is easy enough because because to build a palindrome, we just need to build the first half of the string and then reverse it and tack that on. And then we'll need to be a little bit careful about making sure that the variety constraint is satisfied. But if we but for the most part, like if you look at like the first half of the string alone, and then like even when you reverse it, the variety constraint will still be satisfied. So we just need to make sure that like the locations where the like first half of the string and the second half of the string connect don't like contain 2 consecutive copies of A or C or 3 consecutive B's. We just have to be careful about that. And then for balance, if we know like how many A's, B's, and C's appeared in the first half, then when we reverse it and tack on the end and tack on the second half, all of those will just double, except for if it's like an odd length palindrome, then like the middle element will only appear once. And so if you like build the like left half of the string from left to right, you can easily like maintain both of these conditions and then check if they work for when we like force the string to be a palindrome by building the left half and then reversing it and to create the right end. And so we can subtract those strings out from the total number of strings that satisfy both of the first 2 conditions, and that will get us the answer. This is slightly more efficient than it has to be. Here, like since W goes up to 52, the total number of the total number of strings that work is at most the total number of dynamic programming states is like O of W cubed, and it's actually a little bit, or with a good constant factor, because the numbers of A, B, and C can O of W cubed, and with like a good constant factor because these 3 numbers can like add up to at most W, times 4 different states for variety, and then times like each state will have up to 3 transitions. that gets you like 50 cubed times 12 with a good, or plus like some bonus to the constant factor in total for the first step. And then the palindrome step is actually faster because the strings only go up to length 26. So all in all, this should like work comfortably in time. Probably could even pass for W up to like say 200. Maybe be a little bit close there, and you might run into memory limit issues. In any case, like I think this should like pass without too much trouble as long as you're careful about handling edge cases, particularly in the palindrome computation. Other thing to be slightly careful about is we want to make sure there won't be long overflow, since if you don't think about like the constraints at all, there are like 3 to the 52, which is 6 times 10 to the 24 strings of A's, B's, and C's of length up to 52. In practice, I think this shouldn't be an issue because if you have an A, or because like many of the possible, or of these like 3 to the 52 strings will like pretty quickly violate this variety constraint. And so I think if you just do this DP without thinking hard about it, you still shouldn't run into long overflow. Well, so yeah, I think that's the general idea for this problem. Still like easy to get the details of the DP wrong, but otherwise like conceptually not too bad. I do think if I was one of the strongest teams, I might want to try one of the other problems that's a little bit less error prone first. But I don't know, a lot of the teams have been having some success with K, although H has been catching up. Let's see. So Waterloo just got to Waterloo Gold, that is, just got to 9 problems by finally solving I on their 6th attempt. So congratulations to them. Good to like finally have that problem dealt with. Possible that a clarification got pushed. We're seeing a couple of ACs on I in the queue. So it's possible that a clarification did get pushed, and that's been like helping a couple of teams that were confused get accepted. Yeah, Columbia Team 4 is attempting I. Be interested to see if Harvard takes another shot at it. Purdue attempting I. In general, the scoreboard does like the queue does look a good amount more red than it did at the beginning of the contest, which is to be expected. Now every team is attempting problems that are somewhat harder for them to, a little bit less accessible, and so yeah, it does make some sense that we're seeing a lot more penalty submissions now than we used to. Well, let's talk about how the scoreboard looks for NEC qualification. So, first of all, we'll go to East Central. Here at Carnegie, so the top 5 teams are occupied exclusively by Carnegie Mellon and Waterloo. So, congratulations to both of them. Got a deep bench this year. Notably, this is I think this is very different from how the scoreboard looked last year. I'll pull it up, but I believe last year the top 5 teams came in the East Central Division came from 5 different schools. top 4 teams in East Central last year came from different schools. So this year, Carnegie Mellon and Waterloo looking pretty dominant. So that means that for the guaranteed NEC slots right now, those are going to Carnegie Mellon Team 7, which has a 1 problem plus substantial penalty time lead over Carnegie Mellon 6. And then University of Waterloo Black, which has a large penalty lead over Waterloo Gold, and then a problem lead over Waterloo Red. So those 2 teams are in NAC as of now. Next up in in East Central is Michigan State on 8 problems. They have a better penalty time than Purdue. However, like all of the teams in the top like 15 or so have a like very realistic shot at getting a wild card slot. Just because of the number of like duplicate teams ahead of them. I think last year the wild cards went down to like rank 20 or so in just between East Central and Northeast, and so now we also have Greater New York in the mix. So I think they could go down to I think like NEC slots could go down to like rank 20 to 25. So Michigan State, which like did end up getting H faster than side note, MIT Let Me Register got E. So that on their second try, so they now take back the lead, maintain their lead over the other MIT teams. I think they are. Just show the whole scoreboard for a moment. So now they're back to being 2 problems ahead of the other MIT teams. Now going to be like pretty tough for them to catch up on penalty. I think that like if you, I don't know, maybe just to do an extreme calculation, if MIT Let Me Register were to get both of the remaining 2 problems with no penalties, but at any point in the contest, their penalty would be 809 plus 300 times 2 is about 1400. If MIT Monkey is Typing was to solve all 4 of their remaining problems right now, their penalty time would be 588 plus about 202 times 4 is 1396. So in other words, like the worst case for getting for all killing this contest, if you're MIT like Let Me Register, assuming that you don't like take a bunch of penalties, is about as good as the best case for MIT Monkey is Typing. So if you're one of the like other 2 MIT teams, I think you have to be like thinking pretty seriously at this point about like winning on problems and not on penalty, which may inform your strategy. Like it may mean that you want to like go for some have some team members like work ahead on some of the more difficult problems rather than like trying to get trying to like get the easier remaining problems as quickly as possible. Just because like really what's going to matter is like getting to like 11 or 12 problems by the end of the contest and then hoping that the Let Me Register team stays on 10 or 11. Okay, yeah, so going back to East Central for a moment. Carnegie Mellon, Waterloo first, Michigan State, Purdue, Toronto all seem like they're in a pretty solid position to qualify for NAC as well based off of wild cards. I think Penn State and University of Michigan have a reasonable shot. Probably unlikely that if the score in the current state of the scoreboard, I think the like next school behind them is Windsor, and they're probably out of the qualification range right now. But of course, there's potential for them to solve more of the problems. Looking at Northeast, pull up the scoreboard for them. MIT continues to have the top 3 slots, followed by Northeastern and Boston, with Harvard and Brown right around the borderline for potential NEC qualification. University of Rochester maybe in there. Amherst probably outside of the range right now. And then finally moving on to Greater New York, I believe there might be I think the scoreboard looks reasonably up to date. Are we? Yeah, okay. We're seeing scoreboard updates for Greater New York, so that's all working fine. Now for Greater New York, we have 3 different schools in the top 3. So Princeton, Columbia, and Cornell all doing well. Yale and Columbia already has a team, but Yale in contention for a wild card slot. Rutgers probably a little too far out. so that's where we are right now. The important thing to think about, though, for the rest of the contest is that in a little over half an hour, the scoreboard is going to freeze, and at the 4-hour mark. Oh, by the way, MIT Monkey is typing. Sorry, pausing for a second to take a look at this. MIT is attempting problem L, but they got runtime error. Again, though I mentioned earlier, I think runtime errors are a little bit easier to debug than some of the other verdicts that you can receive on these problems. And so I think there's a pretty good chance that the MIT team will resubmit a bit. Still interesting that they continue not to attempt problem D. So we'll see if they come back to it. Harvard Waffle is attempting problem E. Let's see how they do. But they get wrong answer. Well, will be interesting to see if MIT can become the second team to solve problem L. Anyway, as I was saying, so at the 4-hour mark, the scoreboard will freeze. We'll be able to see who is submitting to each of the remaining problems, but and so we'll see, and so we can get a sense of like what will the scoreboard look like if all of the all of the teams get or as is, but also like if all of these or the other teams get accepted on their pending submissions. But we won't actually know the verdict on any submissions that come in. We'll just know who's submitting. And so that'll create some uncertainty over things like, what the eventual qualification cutoffs will be, as well as obviously assuming that no team all kills the contest within the next half hour, which seems unlikely that these unlikely but not impossible that these teams are going to solve the last 2 problems in the next half hour. Assuming that doesn't happen, though, they there'll be like ambiguity over over who actually is going to win the competition. So we'll see how things shake out. Looking over at the open division, curious to see how the top teams competing unofficially are doing. Looking at so in the open division, Kevin Sun at the 2.5-hour mark has solved 10 problems, everything but J and L. We'll see how they how possible that he's just taking a break or something. Also possible that J and L are just pretty tricky. I think nobody has solved either of them in the open division. Of course, the official teams have solved them. But it does appear that the teams consider C, J, and L to be the 3 hardest problems in this competition. And it's likely that a lot of teams now are setting their sights on trying to get all 9 other problems in order to maximize their chances at qualifying for the NAC. On that note, why don't we talk about problem H? So I will. Actually, we can see both of the top 2 Toronto teams are attempting to get their 9th problems there. One gets time limit wrong, one gets wrong answer. We'll talk about E in a few minutes. I think it's possible that they're running into like a constant factor issue that they'll be able to resolve with or it's also possible that their solution is conceptually incorrect and it'll be harder for them to fix their time limit problems. Alrighty, so so let's pull up problem H. Cool. So we want we're like we're in a situation where this city is restricting creating some rules that restrict slow-moving vehicles from staying on roads that are considered continuous beyond some distance D. So the way this works is we're like listing a bunch of pairs of roads in the town that are considered continuous. And The rule is that like we cannot, or is that a slow-moving vehicle cannot drive on the first road immediately followed by the second road if the total length of the pair is greater than d. Also note that if the second road of one continuous pair is the first road of another continuous pair, then the three roads are collectively considered continuous. So if the path A to B to C is considered continuous and B to C to D is as well, then A to B to C to D is considered continuous. And so there's a fixed D, and we cannot when we're like trying to get from one place to another, we cannot go along any path that stays on a stays on a continuous road for more than d time. So so now, like, given all of this, we're given the specification of the road network, where n is the number of intersections in the town, m is the number of roads, and there's no constraint on m other than that there's at most one road between any two intersections. So m could be like O of n squared. We have like k, which can be up to m times m minus 1 ordered pairs of roads that are considered continuous when driven consecutively. Actually, I might check in on this in a moment. D is the longest distance that slow-moving vehicles can stay on a continuous sequence of roads. And then we're trying to get from some intersection S to T, and we want to check whether it's possible, and if so, output the shortest distance to travel. So I think this problem is like sort of follows the is part of a general like class of problems where where you're trying to do Dijkstra's. There's like some constraint that makes it a little bit trickier. It means you can't just like apply the algorithm directly, but the input constraints are small enough that you can just encode additional information in your state. So if we think about what information we need in order to make sure that we don't stay on a continuous path for distance at least d, the way what we need to know is in addition to knowing what vertex or what intersection, I should say, so what we're calling them here, we're at, we need to know like how much distance we traveled along a continuous sequence already. And then we need to be able to tell for the next road we take, will that be part of the same continuous sequence or will it be start a new one? And the trick here is that that just depends on what the last road we took was. And so if we keep track of like where are we now, what was the last road we took, and how long have we traveled continuously so far, then that's enough to know whether like each possible next step we could take will count as driving on a continuous road for too long. As an aside, by the way, MIT let me submit, and MIT Monkey is typing both made submissions to D and L. No luck there. I do think, like, again, if you're either of these teams, now that you know that you're like sort of trying to win on problems rather than penalty, I do think like my strategy in that situation would adjust to like be less reluctant to submit ideas without being confident they're correct, just because I don't know, I guess there is the constraint of like both of those two teams could like let me register on problems, and then their penalty between each other could matter, but it is just like less likely that that penalty will matter for these teams, which like on the margin makes me want to like submit a little bit more aggressively in order to try to like get through the set as quickly as possible. Anyway, strategy notes aside, back to this problem. So if we have like a state that includes, and I'll try and write this down. Plain text. So if we have a state that includes like current vertex, last road used, and the like value of d, then we have then like the number of states here is n for the current vertices times like n roads that we could have used last. times n values of d. So this takes O of n cubed time. Sorry, this is O of n cubed states. Notice that like, even though there are O of n squared choices for the last road used, and sorry, this should be O of like n squared times d. Notice that like, even though these are they're not coming out of my mouth well right now. Even though there are n squared roads, the like total number of like, or the sum of like all pairs of, or each like road only can end at like 2 vertices. So the total number of pairs of like the vertex where we are now and the last road used is, or can be at most 2m. So maybe like the easier way to write this is like O of m times d. And then each state can have O of n transitions. So this takes O of nmd. The one tricky part is that we have to contend with is that the as an aside, Princeton just got to 9 problems by solving H. Congratulations to them. The other tricky part is if we just implement Dijkstra's, then there will be an extra log factor in here, and n times m times d is about 100 times 100 squared for m times d is 100, which is 10 to the 8th. So then let's start, hold on. Okay, and so if you like add an extra log factor, that'll be too slow. A good way that you can potentially deal with this is by like implementing this by just like having a list of the, or like having a list of the states that we can reach at each of the next 100 distances, and so that will, and then yeah, drawing like your list of states from there rather than like using a priority queue. So in other words, like we can have like 100 vectors storing the states we can reach, storing like where if the current time is t, the vectors store the states we can reach at times t plus 1, t plus 2, up to t plus 100. And I believe like there's still could be some like pathological edge case that makes this a little bit slow. 2-second time limit, which is moderately generous. Also like also like likely that not all states will actually like even be reachable. But like assuming that the states are assuming that like it's impossible to come up with some like crazy pathological output where you actually like have to generate 10 to the like, or you actually have to like do 10 to the 8 transitions or something, this should be fast enough to get accepted, I believe. So I don't know, maybe like cutting out the log factor is the tricky part of this problem for the teams. I don't know, not completely obvious. I think there may be some like other optimizations you can you can do, but I think this should be good enough to pass. Okay, what else is there to talk about with this one? The other thing that's a little bit weird about this problem is K is defined, or is, so M, there's no constraint other than the like implicit constraint coming from that there's at most one road between any 2 intersections. And then K is at most M times M minus 1. The maximum value of M is 100 choose 2, which is about 5,000. So the maximum value of K could be up to 25 million, which traditionally is large enough that you would start to run into IO bottlenecks. So I kind of suspect that there's like some implicit constraint on either M or K that is not in the problem statement, just because otherwise, like unless you have like really optimized IO, like reading 25 million numbers would be a significant bottleneck within 2 seconds. But so I might like ask about that just out of curiosity. Okay, so yeah, I do think it is possible that there are like some additional input or that like the that the problem doesn't even like include the like largest possible inputs, just based on the fact that just based on the fact that you would run into IO bottlenecks if they did, but we'll see. In any case, let's see, anything else to talk about for this problem? I don't think I have too much to add. Yeah, I do think if the actual input k is like less than, or k or m, either m or k is like smaller than the input constraints suggest, then that will be another thing, like making sure that not all of these states are actually reached. And so I do think it's like, even though this theoretically takes O of NMD complexity, which could be a little bit tight, I think it is like unlikely that this like worst case complexity will actually be achieved. Okay. So that is problem H. We can go back to the scoreboard for a bit. I think we just have what problems C, E, J, and L left to talk about, I believe. Let me check if that's right. Yeah, I think that's right. I'll probably do E next in a few minutes. We are 18 minutes away from the scoreboard freeze. Still no teams that have even like attempted to, or an 11th problem yet. Even the two like MIT teams still on 8 solved. Like MIT Monkey is typing still, even if they got both D and L, would be on 10 problems. So it does seem like, other than let me register, the rest of the group is finding J relatively tricky, which I do think J is a pretty intimidating problem. It's definitely not like, if I was reading the set for the first time, it is not the first one that I would attempt. There's a comment in the chat, first of all, saying someone solved problem J in the mirror contest by using, or in runtime, O of n cubed divided by 32 using a bit set. They also mentioned that the guarantee that the 3 edges have to be adjacent, or sorry, the 2 edges have to be adjacent, bounds the input size on problem H. Like they're actually like H, or like for each vertex, there can only be 100 surrounding edges, and so the like total number of pairs for each vertex is 100 choose 2, and so the like total size value of k can be at most 100 times choose 2 times 100, and so the bound is actually tighter than what they give you in the problem statement, and k can be at most like O of 1,000,000. Well, so that makes things a little easier to deal with. I'm curious, doesn't seem totally implausible to me that someone might be able to think of a way to do this faster than big O of like m times d times n. I think that should be fast enough. Okay, so yeah, we are now 15 minutes away from the scoreboard freeze. Submissions are slowing down a little bit. A couple in the last few minutes. We look at the score or the statistics. Let's pull it up. Yeah, so now I think like it looks like the problems can be split into roughly like four-ish difficulty groups, one consisting of A, D, and F, one consisting of B, G, and I, and one consisting of E, H, and K, and then the last and hardest consisting of C, J, and L. So again, like if we think of those as like easy, medium, hard, and super hard, like given where things are right now, again, more and more teams getting to 8 problems, 75 minutes left. So I am growing more confident that you will need to solve 9 problems to qualify for the NEC. It's not a total given. It could be that some of the some of the faster some of the faster 8s slip through. But I do think most of these teams will be able to solve at least one more problem in the last 75 minutes. So I think good chance that the cutoff ends up being 9 problems. And then a lot will come down to like how teams do on these particularly hard problems, C, J, and L. Again, like very possible, or again, like no, I think several teams have one of these 3. None of them have 2. J and L both have one solve each by Carnegie Mellon and MIT. So, like interesting things to watch out for are like which of Carnegie Mellon and MIT can pull off the win? Can anyone else pass them? Waterloo Black would actually be in decent penalty position if they got another problem soon. Still a good amount behind MIT. Other things to notice are for qualification to NAC, they pretty tight battle going on between the top 3 Waterloo teams, the MIT teams, and MIT Monkey is typing now, attempting H, which would be, so they still have D and L in the works somewhere, but we'll see if they can get AC on H. No luck. And then, yeah, the 2 Toronto teams, both very evenly matched with 678 and 693 penalty time. Let's see, how about Purdue? Purdue Fearless is now a little bit ahead as Purdue Frosted Entropy has been on 7 problems for a little while. Yeah, so all in all, things are looking pretty competitive, going to be very close going in. I think once the scoreboard freezes, we'll talk about how the standings look, what the like qualification cutoffs might look like, who's going to be most competitive for the wild cards, that sort of thing. For now, until then, let's do another problem. So let's move on, or let's do the last of the hard problems before we get into the super hard problems. So that would be E. Cool. So problem E is we have this game Chess Solitaire where we're given a board with 2 or more chess pieces, none of which are pawns, and we have to find a series of captures that will remove all but one of these pieces. So if we have M pieces on the board, the solution is going to involve M-1 moves. And we're given an example here. Like, as you can see here, like each move involves one piece capturing another. And then we are given a chess solitaire puzzle and asked to output a series of moves to solve it. So we're given the size of the board, the number of pieces, for each piece we're given what type of piece it is and its location on the board, and we're guaranteed that none of the pieces will be at the same location and all the locations will be formatted validly. And if there's a solution, we just have to output it using like this format they specified for us. Cool. Now, I think like a good thing to note here is, just to flip back for a moment. MIT Monkey's Typing did finally get accepted on problem D, so that brings them up to 9 problems, albeit with a weaker penalty time. So they do still have H among the hard problems left, and then They have solved C, one of the super hard problems. Still have J and L to go. Probably will need, and in order to pass MIT Let Me Register, they will have to eventually solve at least one of J and L. They do already have 2 attempts on L, so we'll see if they can get anywhere. All right, back to this problem. So again, m less than or equal to 10 sort of suggests that we might be able to do some, or to do an exponential time solution. I think the and I think like one thing that we might like naively want or try to do is just like simulate every possible sequence of captures. But with some thinking, like it turns out this is going to be a little bit too slow, because even if you like think, or even if you like fix the like order in which the pieces are captured, we still care about like which position does each or like which piece does each capture. And there are like 10 factorial ways alone, which is about 3 million, to order the like piece captures. And so combining that with the number of ways to choose like which piece does each capture, I think like doing a like brute force try every possible approach is going to be a little bit too slow. So instead, also like MIT, by the way, third wrong answer on problem L, but it does look like that's their focus now after getting accepted on D. So given that we're going to have to do something a little bit smarter, one thing to think about is like, what do we care is like, first of all, at any given time, all of the pieces are going to have to be in one of the like initial piece positions. Like there are like, because every move is a capture, there won't be any state where some piece is at some other position. Also, what we really care about is like which type which type of piece is at each position. In other words, like we don't really care about whether like the bishop that started at A1 or the bishop that started at like A3 is now at position B2. We just care there's a bishop at B2. And so to like encode a like state midway through the problem, the only information we need is what type of piece, if any, is at each cell. And so there are 5 types of pieces, plus it's possible for a vertex to be empty. And so the total number of states is bounded by 6 to the 10, which is about 600,000, I believe. No, it's about 60 million. So this is still a lot. However, in practice, they're going to be far fewer than that, because for example, the number of like pieces of each type has to be less than or equal to the number of pieces that start with that type, which like further reduces the state space pretty substantially. Also, like not all states, like even like or not all like rearrangements of the same pieces will be possible. Like for example, if the like starting state has 2 pieces, a queen in like one spot and a king in another, then like the state where the king is in the first spot and the queen is in the second won't be reachable. So between these two things, it's harder to like get a like systematic evaluation for how many states there are, but it should be small enough that we can feasibly like iterate through all of them in reasonably good time. And then for each state, we can brute force like which piece which like piece captures which other piece. Again, like this adds a bit of this adds like an extra factor, but hopefully shouldn't be too bad. And so then we can do like a sort of like dynamic programming thing where we say like any state with only one piece is winning. Any state with more, or if there are like if there's more than one piece, then we can like iterate over like all pairs of pieces. And if piece A can capture piece B, and if the like state that results from doing that is winning, then we say this state is winning. You can like take this move and then go on to the next state. And then and so this like lets us compute what the like right move to do from each possible state is, and then once we get to the starting state, we're done. So again, you do have to be careful not to like go through a bunch of excess states that we don't actually care about. And how tight is the time limit on this? Time limit is 3 seconds, which is reasonably generous. But I think as long as you like try somewhat hard to like write code in a way that will be reasonably efficient, this should run pretty quickly. So in some sense, like this is, and I think the like ICPC East Division does tend to have at least one of these problems each year where you just like need to do the brute force in a somewhat reasonable way. Here, like I think if you do a completely naive brute force, it's going to end up being far too slow. But if you do a brute force that's slightly less naive, then you can, or then you should be able to get to a reasonable approach. Okay, so yeah, that is all for this problem. Just scoreboard for a bit. IT Monkey is typing now, attempting to solve problem J. So they now have attempts on all 12 problems. This could potentially be the start of their comeback. They do get wrong answer. I do think, like, given that they seem to have ideas for H, J, and L, seems pretty likely that they will get to 11 problems, possible even that they will get all 12. And so the Let Me Register team, even though they're like ahead on a problem, even though they will be far ahead on penalty time if Monkey is typing gets another problem accepted, I think they still like should be a little bit worried and should be trying pretty hard to get to 11 before the end of the contest. MIT now resubmitting J, so potentially they found a pretty quick issue. Again, like if I'm in their position, I'm pretty quick to resubmit even without testing rigorously. Oh, but they do get accepted on problem J, so they now are in third place, just behind Let Me Register. And they now also like notably become the first team to solve 2 of the super hard problems. So if they can figure out what happened with their H, they're in a great position to overtake Let Me Register. Harvard Waffles, meanwhile, like was a little bit lower in the rankings for much of the contest, but now is in 4th place. Finally, dislodges MIT from having all 3 of the of the top slots in the Northeast. Harvard now in 4th place, having solved all problems except J and L. We only have 90 seconds left until the scoreboard freezes, so at that point we won't be able to see anything or any new submissions. So, of course we'll be able to. We won't be able to see the verdicts on any new submissions. We will, of course, be able to see. Actually, is the contest clock frozen? Let's see. There we go. Okay. Yeah. So we won't be able to see any new submissions, meaning that we will. Meaning that like if Monkey is typing submits again, we won't know whether they've actually passed Let Me Register. Likewise, if Let Me Register submits, we won't know whether they got accepted and further their lead. All right, so the scoreboard is now frozen. I'll let it scroll for a little just so we can see like what things are going to look like from here on. hopefully we should be able to see the rest of the board. Yes, now you can see Michigan State just made a submission, and so as you've seen throughout the day, like that turns yellow. Now though, it's not or the result is not going to be revealed. The team will know whether their solution was accepted or not. So if they get it wrong, they will still be able to debug, go back, submit again, all that good stuff. And of course, like if we see them submit again, we'll know that they probably made a mistake the first time. But we won't actually know whether their solution was accepted or not. So we can see. I'll show you like we have a optimistic view of the scoreboard that will like show us this is what the scoreboard would look like if Michigan's submission was accepted. And in general, like this view assumes that all of the frozen submissions, or that for like any team that made a frozen submission to a problem, their last submission was accepted. So this is like sort of a like optimistic view of what the scoreboard could look like. But we don't actually know whether any of those accepted, and we won't until the scoreboard reveal after the contest. In the chat, someone points out an easy way to implement E is to write the backtracking approach going forward in time, but add a visited set to not revisit states that you already visited. Yeah, I think that's roughly how I would implement this as well. You can like even though you can like sort of think about it as a dynamic programming problem, but I do think the easiest way to write it is to like go from the is to like write a recursive function going from the starting state on rather than trying to like go from the like ending states backwards to rather than trying to like go from the ending states backwards. I just think like thinking about these things in terms of their states, which is sort of like DP-esque, makes it easier to reason about like what information do we need to keep track of, like how many states could there possibly be, that sort of thing, which are important questions for this type of approach. MIT let me submit, which now is at a bit of a disadvantage on 8 problems compared to the other MIT team's 10. Did just submit the L for the first time, so see how they do. Lots of submissions coming in after the freeze. Okay, so let's talk about problem C, and then we'll come back and see how the scoreboard looks. So problem C, we are categorizing triangles into 3 types. Acute, meaning all 3 angles are less than 90 degrees. Right, meaning there's a 90-degree angle. Obtuse, meaning there's one angle that's greater than 90 degrees. And degenerate, which means that the 3 points don't form a triangle at all because they're collinear. So we're going to consider all possible ways of choosing 3 distinct vertices from the set of points where x and y are integers, and x is between 0 and some maximum, y is between 0 and some maximum. We know we're given the 2 maxima sum to a most 600. And we have to categorize each of the triangles into one of these 4 categories. Time limit on this, by the way, is 5 seconds, which means that a max x cubed approach should be totally fine. Cool. So how do we count this? One thing to know is that we can easily count the total number of ways to choose 3 distinct vertices from this set. And so one thing that we could do is just count 3 of these categories and then subtract the sum of those 3 categories from the total number of triangles to get the 4th category. So we can sort of think about which of these things is easy to compute. And I think the easiest thing to so I think one thing and so maybe just to start, let's talk about how we would deal with the obtuse triangles. So for an obtuse triangle, we need to have one angle greater than 90 degrees but less than 180 degrees. And sorry, give me just a moment. I'm gonna check on something real quick. Okay. So like one thing we can do is we can just count the number of like triples of points that form an obtuse angle between 90 and 180 degrees, and then that should give us the information that we need. So yeah, pull up a text editor just a moment. So well, this is problem C. So I think like a helpful geometric fact to know is that if angle ABC is obtuse, then if we take like A minus B dot product C minus B, this equals this is equal to like the length of the vector A minus B times the length of the vector C minus B times cos theta, where theta is the angle between these two vectors, which is what we care about. And so really what we care about is counting the number of ways to choose A, B, and C such that the angle between, or such that this like theta is between 90 and 180. And so this, like, a helpful thing to notice is that, or is the like sine of cos theta has a positive sign, or sorry, has sign when theta is between negative 90 and 90 degrees, and the negative sign when theta is between 90 and 270 degrees exclusive. And so if there are 3 points where this computation like gives us a or it gives us a negative sorry, if we have 3 points where this gives us, or where this like dot product is negative, then the angle between these 3 points is between 90 and 270. The main like issue here comes from like whether, I think there's like there is like an orientation issue where if you like where depending on like how you order A, B, and C here, something or sorry, no. Here, like the angle, the theta is just like the smaller angle, so this is just 0 to 90 degrees, and then negative sign when it's between 90 and 180. Sorry, it's been a little bit too long since I've done any geometry. Anyway, so really we just want to, so really like if we count the number of pairs where this dot product is negative, then we will get the or then we'll get at least like the number of obtuse triangles plus the number of degenerate triangles. And then also if we count the number of cases where the dot product is 0, that will get us the number of right triangles. Okay, great. So now if we like expand this dot product out, if we like write A is like XA, YA, and similar, then this dot product is going to be XA minus XB times XC minus XB plus YA minus YB times YC minus YB. And notably, each of these two things is completely independent. Like one just depends on the X's, one just depends on the Y's. So we can count the number of triples of X's such that the X term takes, or that give us each value of the X term. And note that like this can be that like these terms have to be at most like O of max x squared. And similar for y. And so like we can count the number of and so like for each value of the x term, to get right angles, for example, you can count the number of triples that get us this x term value, and the number of triples that get us the negative of this value as our y term. And this gets this gets us the number of triples where the overall dot product is 0, which gets us the number of right angles. And then we can do a similar thing using prefix sums, where we like count the number of triples that get us a specific x term value, and then the number that get us a y value that's like smaller than the negative of this x term value, and that'll get us the number of triples and we can like do that part using prefix sums, and that'll get us the total number of triples where the dot product is negative. So that gets us, so we now can get R and O plus D. And of course we know A plus R plus O plus D, so we know A. And so all that's left is to split the O's from the D's. I believe there are a number of ways you can do this. One idea is to think about like the one idea is to think about like, so like say the three vertices say we have three collinear vertices. Then we can write them as AB, A plus KX, B plus KX, and A plus, I don't know, what's another letter? I don't know, let's say like A plus PX, B plus PY, A plus QX, B plus QY. And so I think if we like fix PX, fix PY, fix QX, then QY is equal to PY times QX slash PX. So QY is uniquely determined. Then we can figure out the then this is enough to like figure out the 3 points, and so we can figure out like what PX, PY, QX, and QY are. And so then we just need to count the number of possible A, B. And this can be done just because we know like, okay, like if QX is or if PX is like 50 and QX is 100, for example, then A has to be at most like the max value of x minus 100, and then we can do a similar computation for the y's. And maybe I guess yeah, so I think that this lets us get the number of collinear points. We have to be like a little bit careful to avoid overcounting, but I think this like ends up not being too difficult. And so this lets us this gets us D in O of mx cubed plus my cubed. I think actually this is like technically O of mx squared my. And so now like we can use that in our computation of O plus D to get O, which is enough to finish the problem. So it's a little tricky. Like I do think that getting the counting right is a little bit difficult. Nice thing is that like aside from knowing the like conceptual ideas around dot products, you don't actually need to do a lot of convoluted geometry to get this, which is pretty nice. If we go back to the scoreboard for a moment, you see that Mungi's typing has submitted, I believe, twice since the scoreboard froze on problem or on problem H. I think they only had one before the freeze. Might have had two. Yeah, they only had one before the scoreboard post, so we know they had one incorrect submission post freeze. We'll see if they're presumably since they submitted again, we'll see if they get right. Carnegie Mellon and the and Let Me Register have not submitted any of the or have not submitted either of the problems that they're missing so far. So that means that if MIT gets H, they'll be in first place. Again, like Let Me Register can effectively take as much of a penalty as they want, like as long as they get, or as long as they like at least tie Monkey is Typing on problems, they'll be ahead. As is, this is pretty close, and we now that Monkey is Typing is submitted, we won't know like which one of them will advance to NAC until the until the scoreboard is revealed. This is worth noting. Looking at the scoreboard, it looks like given that because most of the teams have solved AD and DEF already, there aren't a whole lot of submissions on those. We are seeing some submissions coming in on B, G, and I, as well as H and K, or E, H, and K. Somewhat fewer on the like hardest problems. Still, like only one pending submission from Let Me Submit on problem L, one on C, and then none yet on J. So C, J, and L remain the most challenging problems, but we'll see how the rest of the contest goes. Maybe we can talk for a moment post-freeze about what the NAC qualification statuses look like. Let Me Submit, by the way, resubmitted L, so likely got it wrong on their first try. Monkey is Typing also has 3 wrong submissions. Do you think if you're Let Me Register, there is like a pretty high stakes decision about whether to attempt C or L next? I think, like, just judging by the scoreboard, it seems like C is both easier and that more teams have gotten it, and teams have generally gotten it without taking too much of a penalty, and so it does seem like a pretty logical first one to go for. But hard to say. Also, like worth noting, like the other 2 MIT teams that are attempting L already have solved C. So like it seems, and L is also sort of a geometric problem. So does indicate that like of the 2 geometric problems in the set, those 2 teams seem to view C as being easier. Anyway, so restricting the scoreboard to East Central teams. At the time of the freeze, Carnegie Mellon and Waterloo and Toronto, which did manage to pass Toronto A by solving their 9th problem, are slated for automatic qualification to to NAC. It does look like in terms of wildcards, there are a couple of teams from East Central that are in pretty strong contention. Those being Michigan State, Purdue, and then Penn State a little bit further down, but still has a shot. Let's see. Maybe like we can think about, how many wildcards would it take to get down to like 25th place, let's say. That would from East Central, that would involve Michigan, Purdue, and Penn State and University of Michigan. Purdue. So that would be 4 wildcards for East Central to get there. Interesting. MIT Monkey is Typing, or just attempted L again. Unclear. Like they have had a strategy of just like switching between problems even without getting accepted on the first one. So it might be a slight positive signal that they might have finished H, but it's hard to say. Let Me Register, still no submissions in a while. And then Let Me Submit has been continuing to attempt D, also has a submission on problem L. In any case, assuming the scoreboard does not change, let me register currently in first place, but it does look extremely likely that one of the teams from MIT will qualify. Harvard Waffles has made a pretty impressive comeback from being a little bit behind earlier to take the second NAC slot from the Northeast region. And then third would be Northeastern University. And then if we were to go down to 25th place, University of Rochester, Amherst, and Boston would all get wild cards. So that's 3 wild cards for the Northeast region that it would take to get there. Carnegie Mellon, by the way, just attempted problem C, I think for the first time. Can go back and check. Yep, first time. So that could potentially put them on 11 problems, solidifying their lead. But of course, MIT now Monkey is typing has attempted all 12 problems, so really hard to say who is in first right now. Okay, so finally, looking at the greater New York region, Princeton, Columbia, and Cornell occupying the first few slots. No other teams in the top 25. So if there were 7 wildcards, which I am not guaranteeing, obviously, like that would lead to all the teams up through 25th place qualifying. I think there were 8 last year that we have no guarantee of how many wildcards the East Division will get this year. I think pretty safe to, or I would say it's like none are guaranteed. I think it's like I would be pretty shocked if there were fewer than like 3 to 5, but we'll have to see how things shake out. In any case, though, definitely better to be in the top 5 or top 3 of your region, just so that way you don't have to be or have any uncertainty, since the specific number of wildcards may not be known for weeks or even months. Well, let's see, how are things going now? I think it is time, or I think it's a good time to move over to one of our last 2 problems. So we'll switch to J, which currently has been solved by 2 teams. So one of the silly things about this problem is there are like a lot of pieces in this statement that end up like not actually being that relevant to the solution. So start here. So for a given string S consisting of the letters U, R, D, and L, we're going to say S bar is the string obtained by reversing the S and then swapping U's and D's and L's and R's. And we can prove, like, given some like boundary string B consisting of U, R, D, and L, we can prove that a polyomino can tile the plane by translations if and only if like any cyclic rotation of the string can be written as X, or as like the concatenation of X, Y, Z, X bar, Y bar, Z bar, or X, Y, X bar, Y bar. So it's a neat little factoid. And there may actually be many ways to rotate the boundary string and then write it in one or both of these 2 forms. And then given a boundary string for a polyomino, we have to count the number of ways that each cyclic rotation B of the boundary string can be written as in either of these forms. And of course, if it can't tile the plane, then this count will be 0. And the length of the string is at most 10,000, and we're just given that length in the boundary string. One thing that like it was a little bit confusing to me is whether we're being asked to count the number of ways that like each cyclic rotation can be written in this form, and like each of those counts is the same, or whether we need to like sum this value over all cyclic rotations. I think the problem can be solved using similar approaches either way, but it's not totally obvious to me. Maybe I'll like work out this like sample case here, URR, DLL, just to like see which of these interpretations is right before moving any further. Let's see. So let's see. So I think like if to write it in one of these 2 forms, like first of all, like the first 4 characters are going to be part of like X, Y, and Z, and then the last others will be part of like X bar, Y bar, and Z bar. So I'm just going to like swap U's and D's and L's and R's to get both these strings are U, R, 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 Okay, so then the number of ways to write this is like, right, as x time or x y x bar y bar. I think like in order, since x is being reversed, the like first letter has to be u. Or sorry, the x just has to contain u, because otherwise, like reversing it will change its location. So, so x is u, and so then like one big case is y is RRR, and then the other cases are x bar or r. If we like have both y and z, then we could have x u y r x u, or sorry, x u y r z r r, or x u y r r z r, and so that gives us 4 ways. So I think that we are summing over all possible cyclic shifts, but let me I think there are not 16 ways to do this. I guess yeah, there can't be, because there are only what, like to split 4 characters into 3 non-empty strings, there are only like what 2 ways to, or sorry, 3 ways to do that, plus like another 3 ways to split it into 2 strings. So yeah, so this must be summed over all cyclic rotations. Okay, I feel like that is a little bit confusing. Sorry, just a moment. I'm typing a quick message to the judges. Okay, and maybe like just for completion, we can or we can think about like, or we can make sure that we're like getting the right answer for all of the cyclic rotations. So if we look at RRD LLLU, this becomes when we like reformat it, like UUU, or sorry, the like second, or this can be split into like RRD and RRD. And I think this will work the same way by symmetry. So I think there are 4 ways in this case. If we do like the second cyclic rotation, so we get RRDL, LLUR. The second part becomes RRDL. And here, I think we get 1 way, like because from RRDL. And then last one is, the 4th one is RDLL, LURR, which becomes what? RDLL, RDLL. So, okay, so maybe I'm a little confused. Maybe I'm overcounting something, because I would have thought that like then after because like x or x bar is just x, I think that like after the first like 4 cyclic after the first like 4 cyclic rotations, the rest are all the same, like it's symmetric. So I would have thought it would be like total number of ways would be 4 plus 4 plus 1 plus 1 times 2, which is 20. But empirically that's wrong. So what am I overcounting? So for this version, the like 4 ways that I count are RR, the times operator is concatenation, right? I don't think they like explicitly say that, but surely it must be. RD. Okay, I'm being silly. There are only 3 ways. Whoops. Okay, so now this is a total of 8 ways. And then the last 4 cases double it, so we get times 2, which is 16. Okay, so that works. Cool. All right, so I think like one thing to note here is that like the total length of x, y, and z must be length of s over 2. So that's somewhat helpful. So, and in particular, when we write the string as x, y, z, x bar, y bar, z bar, x and x, or the like start of x and start of x bar must be exactly n over 2, or sorry, size of s over 2 characters apart. So we can sort of check if like for a given substring of s, we can check if it's a valid choice of x, y, or z by looking at the substring of the same length starting size of s over 2 characters away and checking if it's equal to the reverse with UD and LR swapped. Okay, so that's all well and good. That will take a total of, and like importantly, if you hash at the string s, then okay, so if we hash s, then we can check this in O of 1 time. Okay, so we know which sets we care about. Sorry, set which strings we can use, and we need to like figure out the number of ways to pick 3 consecutive strings such that they all sum to or such that they like in sum have length size of s over 2. Okay, let's see, one moment. So I think for this formulation, it's like there's like a relatively straightforward O of n cubed solution where you can like fix the starting point of x and choose starting points for y and z, and this will take O of so this will take O of n cubed time with a somewhat good constant factor. One thing you can do to improve this is to optimize it using a bit set. And so I think one second, sorry. I think the original I originally like interpreted this problem as like this guaranteeing that like each cyclic rotation will be or can be like written the same number of ways, and we just need to find that constant. And so the fact that we're summing over all cyclic rotations makes it a little bit harder, but still doable, I think. Yeah, so an O of n cubed solution is to we just need to check like so this is like so this is an O of n cubed solution. One thing that we can think about instead is like if we fix the string x, we just need to check whether the string starting after x such that, and let's just call this t, such that size of x plus size of t is equal to size of s over 2, can be decomposed into a valid y and a valid z. And one way to do this is to say like yeah, so this I think you can do as a bit set problem by like making a string, or by making a bit set representing like can the string like ending at position t with each length be converted into a valid sorry, can the string ending at or ending at position I with some length become or sorry, is the string ending at position I with some length valid? And then is the string starting at position I with some length valid? I think if you have both of these things, then you can check whether there's like any potential splitting point for a given like, or for a given like total length and a given position by using a bit set. You also, this would add an extra log factor, which is too much. You also could do like but you could also like do something or do this using like polynomial multiplication. Which you might be able to squeeze in. But let's see, is there well, yeah, so I think like if we like, then like for this we can like maybe this is like not the not the like nicest way to do this computation, but I think like roughly the general idea of like you can use two, or you can like shave or fix two values and then shave off a factor of 32 using a bit set should work. Maybe the constant factor is too large. So I think I think you also can get like n squared log n using FFT, and given the 5-second time limit and also the fact that we like only really care about up to 5,000, I think this might all just be fast enough. Maybe that's the right thing to go for. Yeah, okay, like maybe I think the like right way to like decompose it as a bit set is like, so if t is position I dot dot j, then have one bit set storing the k such that I to k is valid, one bit set storing k such that k plus 1 to j is valid, and if like, and then if t of I, or and then if like the and of these bit sets is non-zero, then I to j can be decomposed this way. Alternatively, maybe this is a thinking out loud a little here. Is there a way we can get or make this a little bit more efficient? So this then, like for each I and j, will take like like 5,000 over 32 time roughly. Can we do any better? like for a fixed I, for each j, we want to know, does there exist k such that I to k is valid and k plus 1 to j is valid. There also might be some more observations you can come up with just from the like given structure of the string. Like that is probably a way you can make some progress here. We could also do like a similar bit set idea to like if we fix y, the middle string, we can like you do a like similar-ish bit set thing to check like which values of x and z like containing this y work. I wouldn't be surprised, given that like some of the bit set stuff passes, I would not be surprised if like there's just some tighter bound that we might be able to get on the number of valid strings that like gives us some hidden complexity bonus. I guess for this, like we do actually care about like how many ways there are, which is a little bit annoying. And can be handled using like bit set counts and things like that, but still a little bit tricky to deal with. Okay, hold on. So different. Maybe if we fix y equals I to j, we need count number of valid strings I minus 1 and valid strings ending starting at j plus 1, the same total length. Or with a total length equals like and so in other words, like total length of the string ending at I plus I to be size of S over 2. Plus total length of the string starting at j plus 1 plus j should be equal to size of S over 2 plus 1, or sorry, minus j should be equal to size of S over 2 minus 1. I see. And so now like we can roughly like sum these polynomials over all, or we can like, yeah, we can just solve this using, I think like I need to do a little bit of checking to make sure. Oh, I guess no, it is still annoying because we have to deal with the like fact that I to j has to be a valid string. So we can't just like directly plug this into FFT. Okay, so yeah, my guess is that you should be able to massage something like this to work out. Details are a little bit more annoying than I realized just because of the like way the problem description was phrased. Maybe just talk for a little bit about L, and then we'll close by looking at the scoreboard again. So we have this like piecewise 2D model where we have like some points and we're just connecting the dots. And we also have some fixed locations that contain nests for these rare birds. And rain is going to fall at some fixed rate, and we need to figure out the amount of time it'll take before each of the nests is under the rain. So I think like the main tricky thing that comes up here is that the like lower points are not necessarily going to get rained on first. Like in the sample input, this triangle over to the left is going to get filled up, and then the water is going to go from there to the right to help like fill in this larger triangle. I do think like so I think that makes things a little bit annoying to get right. I do think like roughly what you want to do is just like simulate the process, keep track of like the current level of water within each triangle, and then and then like update the like rate at which water is filling as the as water fills, just like inserting a breakpoint each time the water fills enough to like sort of merge two triangles. So once you like these two triangles are both filled, for example, they merge, and then water is like filling this trapezoid up here. And so I think like this is like very easy to get wrong, like lots of implementation issues that can come up, but you should end up getting the right answer. It also helps that the like number of points in the piecewise connection is at most 50, which means that you can do a pretty brute force simulation and it should still work out okay. All right, so going back to the scoreboard for the last 10 minutes. So Monkey Typing remains the only team to have attempted the all 12 problems. Let Me Register has not made any further submissions, so if they aren't able to solve any of the last two problems, then it appears pretty likely that Monkey is Typing will have passed them and qualified for NEC. Monkey is Typing actually did just resubmit their H, so it does look like they might have not gotten accepted on that yet. It's a tricky spot for them. I do think that in the last hour with their situation, it probably makes sense to just focus on one problem. If they haven't gotten either of them accepted, but it's also possible they already have AC on L. They could even have AC on both problems and are just trying to mess with us a little by resubmitting to a problem they've already solved. Hard to say. Other than that, we can look at what the optimistic version of the scoreboard would look like. Here, you can see if every team that has submitted so far is in fact correct, then our Monkey is Typing would win the contest, followed by Carnegie Mellon, Let Me Submit. Both MIT teams actually passing Let Me Register, and then Rochester making lots of extra submissions in the last few minutes would be in fourth. course, like this is unlikely to be what will actually happen. Many of the pending submissions will be incorrect, but we'll just have to see how it turns out. It does look like a good number of teams on 8 problems have made no further submissions. Some of the teams on 7 might get 2, but it does look like at least some of the teams on 8 problems will at least have a decent shot at getting a wild card for the NAC. Just have to see how things turn out. Okay, so word in the chat from people who have who are doing the open contest is that I think you can for J you can like squeeze O of n cubed using bit set. There also is a an O of n squared solution that like thinks conceptually about what the or about the behavior given or about like the structure of the strings as representing a polyomino. We have about 7 minutes left in the contest. Toronto B just attempted their 10th problem. Does look like C, J, and L all remain relatively unsolved. So, and it looks like much of the activity comes from comes from teams finishing up E and H. If we go back to we let the scoreboard scroll a little, we can see how things look elsewhere. University of Rochester in 20th just resubmitted E. lots of submissions lower on the scoreboard, which is nice to see. Teams still have plenty to work on. Still teams going for their second, third problem. All right, so let's go back to the top. Taking a final look at like any interesting NEC qualification scenarios we have going on. So in East Central, let's see, Carnegie Mellon, Waterloo, and Toronto. They're in a pretty good state on 9 problems with good penalty time. Michigan State could potentially make it close with Toronto. Either way, though, those teams likely to get wild cards. Similar for Purdue. Lots of potential though for, I don't know, like McMaster is an interesting team to watch. If they get accepted on K, they could potentially move up a good amount. And make their way into the qualification slots for looking to Northeast again. Like some potential for teams like Amherst, Boston, Brown to improve their situation and move into the any slot range. And then finally for Greater New York, so we've still got Princeton, Columbia, and Cornell in first, second, and third. Yale does have 2 pending submissions, so could potentially move ahead. However, they have 14 attempts on H, so might not have the best penalty if they get that accepted, but also possible that they got H earlier and are just resubmitting to be a little misleading to other teams. All right, so going back to the overall scoreboard, again, here's the optimistic view. Looks like SUNY is just submitted to every problem just for fun. Good for them. Lots of potential for things to move around. Will depend heavily on how the scoreboard reveal goes. I think we are in a fun situation where any of the 3 MIT teams could theoretically be the one that qualifies for NAC. So we'll be excited to see how the reveal goes. Bit unfortunate that Let Me Register still hasn't been able to crack either C or L. Does like give Monkey is Typing a little bit more of an edge, but we'll just have to see whether they can or whether the other teams can actually get accepted on the problems they've attempted. Harvard Waffles submitted 2 times to J in quick succession. Might have caught a quick bug and then realized. Let's see. So 10 seconds left until the contest ends. Frozen, that's unfortunate timing. 2-1. And the contest is over. Lots of last second submissions. See who the looks like Montreal got the last submission of the contest. We'll have to wait to see who actually got the last accepted submission of the contest. In any case, that is where that is the end of the contest. So congratulations to all the participating teams. We're going to take a break in a minute or two. We'll be back in roughly 20-ish minutes with the closing ceremony. So stay tuned for that. I think we'll have a scoreboard reveal, at least for the greater New York region. Not sure whether it will include the Northeast or East Central regions. And just to clarify, someone's asking in the chat if I leaked the leaderboard. No, I do not have access to the final results. The view that you saw a few minutes ago was an optimistic view for if all of the pending submissions were accepted. That is likely not going to be the outcome. Some of the pending submissions will be rejected. But the exact status will just be revealed at the closing ceremony. So we'll just have to wait until then to see how things turned out. All right, so that seems like a pretty good stopping point. So from here, going to take a quick break, and then we will be back with the closing ceremony shortly.
in their region, in their area. So we would like to honor at this time Professor Liam Kelleher from Mount Allison University in New Brunswick in Canada. Liam has been a coach at Mount Allison for many years. He's been a judge. He wrote some of your favorite problems from this year's competition, as well as past competitions. He organizes a competition every year at Mount Allison. He does great work in Atlantic Canada in organizing teams and other competitions there. And we're incredibly privileged to have Liam work with us. He usually shows up to judging behind the scenes with complete problems already done with multiple solutions and all the test cases and says, how about this one? And it's like, yes, please, thank you very much. Not to mention all of his efforts, helping all of us be the best problem writers we can. So we're very, very excited to have Liam as part of our team and to be able to nominate him for this honor.
So Liam, congratulations, and please join me in
And he is, I hope there at the site at the University of Moncton, we were speaking to him earlier. Not that we told him about this, he did not know this was coming. Now, having done that, just remind you that the advance to the North American Championships, there will be 3 guaranteed slots from the Northeast region, which at a maximum of 1 per university. And there are 3 additional slots that will be shared across the East Division. Those ones will get announced later. We have to kind of, merge the scoreboards of the different regions and all of that. So we will only be announcing the 3 NENA slots at this time. And in order to find out who won those slots, let's go to the resolver. So let me get this up and running. And now, there was one year when my computer was not happy to do a Zoom share and a resolver at the same time. We shall see how it appreciates it this year. The answer is maybe not. Okay, here at RIT, it is a little on the small side, but hopefully for those of you in other sites, you can see it. So we'll see how that looks.
That's what it looks like.
It looks like here. Okay. So as you see, the scoreboard froze with 1 hour left and 301 pending submissions. These are all the things in blue, and this was the standings at the time that the scoreboard froze. And we have a nice big region with close to 100 teams in it. So, all of you who were doing well today, again, realize how many teams you were competing against. It was an excellent job. So what we will do here is we will go through these submissions that came in the last hour and see what happens. The Memorial University of Newfoundland's Team 2 had a submission to problem B and one to problem D that were not correct, unfortunately. The University of New Brunswick Team 3, their solution was incorrect. Sienna Green had an incorrect solution. University of Montreal had a solution, and that was correct, and they move up the scoreboard now having 3 correct problems. Memorial University Team 3, incorrect. Wellesley's Goose Overflow had 2 correct answers. Good for them. University of Moncton's Triple Ninjas submitted to problem F and got it correct and moved up the scoreboard. RPI's OZ also has a correct submission. Yahalo World has an incorrect submission, but 1 correct. The Pink Griffins have a correct submission. A lot of success here in the last hour. Very impressive. Wellesley College O of 1, no bugs. Unfortunately, did have 1 bug. But we appreciate your optimism, and we love your enthusiasm. The Caddis Crackers did not get a correct answer. University of Montreal 5 had 3 problems correct, as did Moncton's Triple Ninjas. Yahalo World got a 4th problem, and they zoom up to the 50th place. RPI's ORS also correct, and they zoom up to 50th. McGill Purple had 3 submissions in the last hour. Usually the ones that come in at minute 299, yeah, those don't have a high success rate, but you never know. It has happened. Unfortunately, the submissions to KNL were also incorrect. UDM 4, an incorrect submission to problem G. Olin Engineers 2 have 3 answers correct. Sienna Gold with 3 correct answers. University of New Brunswick Team 2, a correct answer, and up the board they go. Panda Express, 29 incorrect submissions to problem C, but good on you for trying. Problem G they did not get, but after 23 attempts, they did get problem I. So that still is a correct submission, and up they go. So persistence is rewarded. The seg faults, an incorrect answer and an incorrect answer, and they stay with 3 submissions. McGill's NERV, an incorrect submission, and another one. Oswego Green, no submissions in the last hour. Harvard 6, 7, yes, fine. An incorrect submission to problem I. Moncton syscalls or bloat, an incorrect submission to their 2 problems in the last hour. McGill Burgundy, an incorrect submission. Trevon Quavius at OPI had a submission, and that was correct, and they move up the board. Team with 3 correct answers. The T-Dogs with 3 correct answers. The Boss with 3. Montreal 2 with 3 correct answers. UPEI Panthers Rust with 3 correct answers. RIT 5 had 2 attempts in the last hour, incorrect on G and incorrect on I. The Bulldogs, 3 problems solved. The Lizard Wizards with a 4th problem in the last hour, and they go up the board. Olin Engineers 1 with a correct answer. Big O of Win did not win at this time. Your future is still ahead of you. The PEI Panthers Green, incorrect and with 3 problems solved. Dalhousie, the Final Symphony with 3. The Exabytes on G and I, they got right, so they move up. Potato Toe, I definitely should have practiced some of this. They stay with 3 correct answers. The Roblox from Union have 3 answers. Mammoths 2 with 3. The Puppies, pretty good for puppies, 3 correct answers. The SMU Code Husky Mission submitted to I and got it right, and they move up. Prize Cutoff, they move up. And now we have some teams here with 4 correct answers. So McGill's Yahala World, OPI's Oars. University of New Brunswick has a 5th answer correct. Panda Express with 4. UNB Team 1 with 4. Trevon Quavius. The Olin Engineers get a 5th problem. Harvard 2 with 4 problems. Concordia with 4 problems. The Lizard Wizards. The Sneaky Golem at Northeastern. UMass HKG with 4 problems correct. The Exabytes with 4 problems correct. St. Mary's with 4. Prize Cutoff, they're trying some more, but they stick here with 4 problems. Rochester Blue has 1 more attempt. 4 problems solved for them. Hyper Hog Log, okay, at Northeastern gets a 5th problem and they move up. The Dalmatians, a 5th problem solved. Value Exception, a 5th problem solved. And we got a lot of success here in this last hour. UMass LL Mao, a 4th problem, 4 problems correct. RIT 2, a correct submission to problem B, and they slide up the board. McGill Chartreuse gets 4th problem. Northeastern Dart Goggins has 4. RIT 3 with 4 problems. McGill Vermilion with 5, and they move up. McGill Yellow has 2 attempts, and they move up. The Charlies and the Sowl move up. The Whoopers, they stick here with 4 solved. Mount Allison's Binary Bears also stay here. And that brings us to the teams with 5 solutions. UNB Team 2, Olin 1, the Dalmatians, the Hyper Hoglog, the Value Exception, and Brown Team 2, they could move up still. And they do. Into the 18th position. Very well done. OPI is looking for a job. Well, they're putting on a good show. They're looking well, and they move up with a 6th problem solved. RIT2 also gets a 6th problem correct and move up. McGill Vermilion stays with 5. McGill Orange has a 6th problem. McGill Yellow and the Charlies and the Soul are done. RIT 4 is done with 5 problems solved. McGill Blue with a 6th problem. Northeastern Log Bait with a 6th problem. Touchdown Draft with a 6th problem. The Runtime Terrors stay with 5 problems solved. No code found exception, 5 problems solved. Memorial University Team 1. No more problems solved, but they are finishing with 5 problems solved. Union's Minecraft with 5 problems solved. McGill Aquamarine, you guys you have a lot of colors. I'm very impressed. With 5 problems solved. Concave from Concordia. They solved problem K in the last hour and they have 6 solved. So now we are up to the teams with 6. Looking for job. Brown Team 2 with 6. Well done. RIT 2 also with 6. McGill Orange and McGill Blue with 6. Northeastern's Touchdown Draft with 6. Northeastern's Log Bait, they have 7 and they're up into the top 12. We'll see them again. McGill Green with 6. Concave with 6. McGreedy with 6. RIT 1 with 6 and with 5 additional submissions in the last hour. We'll see how many of those pan out. Well, not problem C, but problem E. They moved up to the 10th place. McGill Red with 6 and the 7th for them, and they're in 11th. UMass Try Our Best. Well, they tried their best and they got 6 problems solved. Well done. 200 WPM, 200 words a minute is enough to solve 6 problems. I guess the rest of you got to type faster. Log Bait finishes with 7 problems, and we're now moving right up near the top. Brown Team 3. And you can see here that they were, in fact, the first team in both regions to solve problem D. That's what the dark green there is on problem D in 11 minutes. So congratulations to them. They have 7 problems solved, and they're not done. They tried 2 more solutions, and they did, and they move up into 8th place. The Harvard undergraduate qualitative traders, they did not get that one right, but they did get H, and now they have 8 problems. McGill Red with 7. RIT1 is back. Let's see how they did on the rest of these problems. On problem H, it was not correct. Problem J was not correct. Problem K was correct, and they move up into 7th place. Brown Team 1, you can see, was the first to solve problem A, a little leftover pizza, in 3 minutes. So well done to them. They also attempted problem E at the end and problem H. Unfortunately, those were not correct, and they finish with 7 problems solved in 12th place. So well done. The Boston Terriers. I thought I got rid of those. I thought I left these out of the system here, but apparently I did not. Apparently they're here. So congratulations to those guys. Because yeah, the resolver is a thing of great mystery. Okay. Well, there we go. I mean, deserved success. The Boston Terriers solved problem E in the last hour with only 8 minutes left, and that bops them up into 6th place. Brown Team 3, as we said, they were the first to solve problem D, and they have solved 8 problems overall, so well done to them. The Harvard Qualitative Traders, no more submissions for them, but in 10th place overall, so congratulations to them. Mammoths 1 from Amherst College, an excellent showing from them. They have 8 problems already and a chance to add a 9th. And they do, moving up into 6th place. So very well done for them. And that leaves us now RIT1, having done as much as they could, finishing in 9th place. So congratulations to them. Now we have our trollest opponent with 8 correct submissions and 2 more attempts in the last 4 minutes. Let's see if either of those panned out. Well, the problem C did not. Problem E also did not. So they stay here in 8th position, but an excellent job nonetheless, with 8 problems solved. The Boston Terriers have 8. Now let's look carefully. As I said, only one team per university can advance. There is one well-represented university here at the top of the standings. And perhaps we wouldn't be surprised by that, but that means that at the moment, it looks like MIT, Harvard, and Northeastern will be those teams, but we are not yet confirmed until we see this result. Are the Boston Terriers going to move up? They are, but it is not quite enough. They finished just behind Northeastern. So the Mammoths in 7th place from Amherst College, an excellent showing. The Terriers in 6th, just 5 penalty minutes behind Northeastern University's Bridge Spam in 5th. So congratulations to the Boston Terriers and congratulations to Northeastern University. Team Bridge Spam, the team from the 3rd highest university at the Northeast North America Regional this year. So congratulations to you and the advancement to the North American Championships. We now have Let Me Submit from MIT. You can see here they in fact did continue to submit, so we did let them. And they have submissions to problem H and problem K. Problem H came in, and that was not correct. Problem K came in, and that was, and they move into 3rd place. The Harvard Waffles have a submission to problem J in the very last minute. And unfortunately, like most last-minute submissions, it did not pan out, but an excellent attempt for them. They were also the first across both regions to solve problem G, and having solved 10 problems and finishing in 4th place, they have also earned the advancement to the North American Championships. Let Me Submit, the first to solve problem C. Oh, sorry, I take it back. It is the Northeast first to solve, because as we'll see a lot of first to solve very soon. Let Me Submit was the first to solve problem C and solving 10 problems overall. They are in the 3rd position, so congratulations to them. Monkey is Typing is currently in 2nd and not by very much, and they have 2 more submissions. How did they do? Problem H was a success. With 10 minutes left in the competition, they move ahead with 11 problems solved. So congratulations to them. That leaves Let Me Register 6 as the first to solve problem H, the first to solve problem J, the first to solve problem K, having solved 10 problems overall. They are in 2nd place overall, so congratulations to them. There's still one more question. Monkey is Typing has solved 11 problems, and they have a submission to the 12th. Did they, in fact, complete the entire contest? First to solve problem 12. Monkey is Typing. First to solve B, E, F, I, and L, solving all 12 problems with 10 minutes left in the contest. As one of the judges, I can say that's just exactly what we aim for, is one team to exactly finish at the end of the competition. So thank you to Monkey is Typing for making the judges look good. And thanks to all who competed. It was a super fun event. I hope you guys had a lot of fun, and we had a lot of fun helping it happen. At this point, I'm going to stop the share here. I'm going to bring in Ivona Bezakova, the regional contest director, to say a few final words.
Just very few. Thank you all for competing. I hope you had a great time, and we hope to see you next year. Bring friends, and great job. Good luck, and that's it.
from many different communities come together to one place to compete against each other and create a community.
Many different recording involved in the same competitions here. I met some of my closest friends through these competitions, and to this day, I'm still very excited to lose.
I have been competing in ICPC for 10 years. What introduced me to the problems
Different. I think it's very hard to something small. They are this experience led to me lose so much away. So I really thought of expertise in my
Thank you, James. Support and putting on content all around North America. So thank you. NSA. So while we await the final minutes of the resolver, I wanted to invite back up here and for a little talk, little Q&A for anybody. And I'm sure he can answer all your questions.
All of them. That's
all of the questions. And I will check on the resolver and hopefully we'll be done soon.
great. Thank you. And you will stay close in your. All right. So there's space for questions. This can range in any direction. I don't care where it's gonna head, but I might say no. Fire away.
Okay, so in previous PNYR content, which I've seen the problem sets on, these problems are often those you can reduce to like a tree or a string or an array, and then either you can just find a mathematical formula for it, or you can use recursion. And most of these problems are like quite unusual, where you have to like find a number pyramid which you couldn't easily simplify, or brute force solitaire chess, which was crazy. with problems where you couldn't use some mathematical argument where you just reframe it into like
That's not part of the question. But also, I do not qualify to answer. Remember, I was in a spook break though. Actually, it's a good question. I'm sorry, is there someone who can answer this?
I think all the people involved with making the contest are in the other room finalizing the results right now.
I'm sorry. I would love to answer for you. I cannot. Other questions? More questions? More questions in other directions? Yes?
What's your favorite feature about Conference?
Oh, my favorite feature about Conference. It sounds like you're hired here. I think my favorite feature it's technical features. I'll skip that. Well, it's coded. It's also a bit. Okay, the one that is easiest for people to maybe understand, people might actually recognize it, is actually null safety. I personally really like if a language makes it impossible to throw null pointer exceptions by design. That is something that I think is very big, and a lot of modern languages are actually going in this direction. Even C# has this now. optional, and most people who now getting into C# are actually disabling in most modules or enabling null safety, which gets them decent guarantees. And Kotlin had this from the get-go, which is great. Otherwise, coroutines, but there's no. I'm gonna derail. I'm gonna get derailed if I start about coroutines. So that is an amazing question.
Thank you.
Listen, Tim, that's the kind of questions I would love. Thank you. Yes. More questions.
Why have your like IDEs separated by language? Like, why not offer kind of one IDE that?
So all languages, they have their, or it's not necessarily per language, it's more like per ecosystem. For example, IntelliJ is JVM based languages, where Kotlin, for example, is mostly JVM based. Or most popular started JVM based. There's Scala, there's Groovy. Those are, for example, in IntelliJ. And this is an ecosystem. So they have their own build tools, their own packaging, they have their own library host provider thing, term that I lost. And these ecosystems have their own UX, their own flows. If you would put all the intelligence we have in a single IDE, it would be to make it a good UX. And yeah, no, I'm gonna geek out there. But that's most of it. And otherwise, you can actually, for quite some of the features, if you get IntelliJ, you can plug in a lot. You can just add JavaScript bundles. You can add even C support nowadays. It's quite decent, and it's technologically actually quite impressive. But that's another story. Thanks for the question. More questions? Yes.
Well, why would you recommend like interning at JetBrains?
Interning at JetBrains. That is a really good question and a little bit of an awkward question. Because currently in this cycle, we only accept people who legally can work in Europe without a visa. And that excludes a lot of people here, I'm afraid. But if you can legally work in Europe, for careers, this is different. But for internships, if you don't need a visa to work in EU countries or in Serbia or in Cyprus, then we happily take you. We will fly you over. We'll give you accommodation, and you can do an internship with us, which is a really cool opportunity. Which I'm not going to hype up too much right now because I might be a little bit salty for people. Thanks for the question, though. More questions? Are we on the resolving?
We're ready to go.
Ready to go. Oh, we are ready. Oh, I was overdoing it.
But not for some.
Oh yeah.
All right, everybody, just before we're about ready to start this, I just want to thank our volunteers, everybody, where are our volunteers? We have a few here, right? Stand up, jump up and down. Thank our site director, Christian Lim. He's not here right now, but Josh is filling in. I think we did a good job here. I hope you guys had fun and it was nice and challenging. And I also want to thank all of our New York team here that puts in so much work to make this happen. So thank you, everyone. Okay, I go now, and pass it along to the Resolver Master.
Okay. Thanks, Joe. Okay. So I know most of you have probably seen the ICPC Resolver before. Maybe some of you haven't. So this is the tool that we use to find out what happened during the last hour of the contest.
You realize though, if you do this, I don't have to do it anymore. You have to come back every year and do the resolver.
I
usually do it now.
No. Blame him. He's the one who said I had to do it. Okay, so during the last hour alone, there were 227 submissions from teams. At the start of the last hour, this is what the scoreboard looked like. Okay, so when the scoreboard was frozen, this is what we saw at the top. And again, as you've seen scoreboards, green means it was successful, red means it was a non-successful submission, and now blue means it's a pending run on problems. Yeah. So what we're going to do now is we're going to go all the way down to the other end of the scoreboard.
Sorry, one minor announcement. We're giving away additional awards that may pop up anywhere here. First, second, and third place, you take your medals home with you. Anyone else that's winning an award, you take a photograph with us with that award. We take that medal back, and I will ship you your award in a week. Because we come up with some nice awards, different categories. So every year is different. So we're having a little fun with it. Anyway.
And one that we did not mention is that this year JetBrains is here and they are going to present performance awards to the top performing teams here. So when we get to the top, you will see we'll stop and have a number of awards for teams. Okay, to start with, let me apologize if I mispronounce any names. I do this at the World Finals, and this should be a piece of cake compared to the World Finals. Because at least all of you speak English. Okay. So at the freeze point in the contest, at the bottom of the scoreboard currently was Thoreau W2 team. I want you to notice that in these things, the numbers here tell you how many submissions were made, at what time that submission. We're going to start off with Thoreau, team 3. I'm sorry, team W2, and they submitted it, and it was because of that. All right. All right, now we go back. Oh, I see. We have to recollect them so that they can be properly rated and open. And of course, we didn't know until right now that they got the Perseverance Award. So we have to go back and do that. Okay. So now, moving on, we're going to see what the rest of the teams moving upward to the medalists. The NCC jump outs have no pending runs, so they're done. The Thoreau LCM 1 team is finished. The NCC seg faults are done. Thoreau W1, we just saw them. Columbia 19, no runs there, done. Hofstra Pride 2, they Hofstra Pride 1 is finished. Pride 2, they get a no from the judges. They're finished. Rutgers, the Three Students. One team gets a no, they're finished. Columbia 15 has no runs, they're done. NYU team 5 gets a no, they're finished. Columbia 16 has no more runs. NCC Columbia 8 gets a no. The NCC 617, great name, guy. Queens College Purdue is done. Columbia 13 is finished. Cooper A, no more runs. They're finished. Queens College team 1 is done. Princeton 5 has 2 problems. Burning machines are done. The Poly 4 team gets a no from the judges. They're finished. Thoreau W3 team is done. NYU team 6 has the judges reject that one. Columbia 18 has 2. First one's a no. The second one's a yes. Princeton 4 has 2 pending problems. Columbia 12, first of theirs is a no. The second one's also a no. They're finished. Poly 5 has 2 problems. First one's a no. The second one's also a no. They're finished. Columbia team 10 has no more pending runs. NYU team 2 gets a no and another no. They're finished. Columbia 8 has no more runs. They're done. Princeton 5 has a submission and it's a no. They're finished. Columbia 18 has none. The 100 plus. And 4 is finished. Columbia 9 gets likely triple double gets a no, and they're finished. 4 is finished. The Stony Brook Gym Bros get a no. They're finished. The Stony Brook Team D, they get a yes. Ball Masters, they get a no from the judges. Columbia 14, 2 problems. The first one's a no. The second one's a yes. The Persian team has 2 problems. The first one, was a yes and a. Columbia 7 gets a yes. Team has 3 problems. The first one's a no. The second one's a yes. Altruistic algorithm, 2 problems. The first one's a yes. The Cook Plus team gets a no from the judges. They're finished. The Cornell Min Fams, 2 problems. The first one's a no. The second one's a no. They're done. Columbia 9 has no more runs. They're finished. Columbia 17 gets a no from the judges. They're done. The Stony Brook team has no more problems. They're finished. Columbia 5 gets a yes. The Dolphin team. Virgin is finished. Columbia 7 has a pending run in. Likely unnamed. No more runs. They're done. NYU team 3 is finished. Cornell altruistic algorithm. They get a yes. Stony Brook team E. They move up also. Sunnybrook Team A, they get a yes and no. Cornell Beta gets a no from the judges. They're finished. Columbia 11 has no more runs. They're done. The Stony Brook team is finished. The Poly 3 team has 2 problems. The first one's a no. The second one's a yes. Columbia 6 gets a yes, and they move up into the top. Poly 1 team gets a no from the judges. They're finished. The Poly 2 team is done. The Yale Ladybug team has 2 problems. The first one's a no. And the Yale Monkey team has 1, and it's a no, but we stopped here because we want to acknowledge, first of all, stand up. Stand up. Okay. All right. Thank you, guys. Okay, let's see. Moving on. We're moving now into teams that have solved at least 6 problems. Let's see. The Columbia 7 team has no more pending runs, so they're finished. Columbia 5 has none, so they're done. The Yale Dolphin team has a submission on problem 8, but it was a no from the judges. The Stony Brook Team E is finished. The Rutgers Likely Unnamed is done. Cornell Altruistic Algorithm is finished. Stony Brook Team A has none, and they're done. Poly 3 is finished. The Food team from NJIT has 2. The first one's a no, and the second one's a no, but we do want to acknowledge, please stand up. They were the first one. All right, now we're in the top 20. Let's see, we've got the Yale Ladybug team. They have no more pending runs. They're finished. The Columbia 6 team is done. The Columbia 3 team has 2 pending problems. The first one's a no, the second one's a no, so they're finished. Columbia 4 has 1, and they get a no from the judges. They're done. The Princeton 1 team has 2. The first one's a no, the second one's a no. The Rutgers Likely AI team gets a no from the judges, but please stand up. All right, into the top 15 now. Let's see, what do we got? We got the Princeton 3 team with 1 pending problem. It's a no from the judges. They're finished. The Yale AWE team has 3 pending runs on problems. So let's look at the first one. The first one, it's a yes. They still have pending runs on 2 more problems up there. So the Yale Whale team, they are currently in 12th place. They have pending runs on 2 different problems, E and K. Let's take a look at the first one. That's okay, we're in the top 4. This is, oh, okay. Notice where we are right now. This team, remember I told you that this is how many submissions, and this is the time. Can you do the math? 5 hours, 12, counting from 0. That was submitted in the last minute of the contest. Run out there. So we'll go back. The NYU code dependence team. 24 submissions on, and the last one at 298. Unfortunately, it was a no. All right, so we'll go on Columbia 1. They have pending submissions on problem K. We'll take a look at that. And that's a yes. All the teams out here at the top that still have pending runs, and we're looking for the top 3 teams, medalists and advancement to the North America Championship. let's see, we go back to Yale WE team, pending runs. Remember, this is the one that had the, oh, no. Yeah, oh, no, that was the other, yeah, that was these guys right here, okay. But let's take a look at the Yale AWE team. They have pending runs on problem H. That's unfortunately a no. They also have pending runs on problem K. That one unfortunately is also a no. But we're going to stop here because finishing in 11th place and solving 7 problems while they are freshmen. I want to point out, they are also the winner of our first JetBrains Performance Award. So congratulations. Oh, God. Yeah. Okay. Yeah. Move down this way. Are we straight down this way? Okay. Got it. Yeah, you got it. That's how you all right. Freshman, sophomore team, boy, we're looking forward to several more years of competition from that team. All right, so now we're looking at the top 10, and all the remaining teams have solved 7 or more problems. In 10th place, Princeton 1 team, they have no more pending runs, so that means they have earned the JetBrains Performance Award. Come on up. Yeah. Ready? Okay. All right. Yeah. We have all these things here. Perfect. All right. This is. Oh, yeah. Okay. All right. The Yale Zookeepers. If you remember earlier, I pointed out the fact that they got the 299, right? That was that one, and they still have one more problem. So we'll see what happens with that. This thing. All right, back down to 9th place currently, the Yale Whale team with pending runs on problem K. And let's see if they get it. This is exhausting. This is worse than the World Finals. You got Bill at the World Finals. Yeah, right. That's true. You're supposed to come over here right now and tell me you want to rearrange. Okay. Okay, currently in 9th place, solving 7 problems, but with pending runs on problem E, Columbia 2 team. Let's see what happens here. And they get back down the Columbia 1 team. They have no more pending runs, but they have earned the JetBrains Performance Award. Okay. Wow, they went home. They went home. Yeah. Tell me, did your team go home?
Yeah, I know. And we lost them.
Okay.
Yeah.
Okay, well, we take credit for all three of them. Over here. Yeah, slide down here. All right. All right, so moving on, the Rutgers Pew Right team, they have no more pending runs, so finishing in 8th place, solving 7 problems and earning a JetBrains Performance Award.
There we go. All right. 1, 2, 3. All right.
Okay, currently in 7th place, the Yale Bumblebee team, having solved 7 problems, but with pending runs on 2 different problems. The first one is problem H. Let's see how they did on that. No, that's a no. Okay, they've got a pending run on problem L, and notice the time stamp on that. 299. Notice, I don't know if you've been paid attention. It was the only submission in that problem, right? So let's see, was the no. That does mean that they finished with the JetBrains Performance Award.
Good.
And here we go, back to the Yale Zookeepers. They have no more pending runs, but
They were always fun.
yeah, they were the team. Notice in column E there, they were the team with the 299, and so they get the photo finish.
Point out that the photo finish last one to do sentence.
Yeah, there were several teams that submitted in the last minute, but they were the team that submitted the last accepted run in the contest.
Wow. Well, that's not quite accurate, but
It's close.
All right, bring up those smiles again. 1, 2, 3. There we go.
Yeah.
All right, so moving on to Yale Whale team in 5th place, solving 8 problems, no more submissions, and so that means they also earned the JetBrains. Okay.
Yeah.
Right.
There's 1, 2, 3. Got it.
Okay, we got, okay, all right. So by now you all know how to read the Resolver scoreboard, and so you know that the Columbia 2 team with no more pending runs means they finish in 4th place, solving 8 problems, and they have earned the Jet Break.
Okay. 1, 2, 3. Perfect.
So, as I mentioned, one of the purposes of the Greater New York Regional Contest is to select teams to go to the North America Championship. And at a minimum, the top 3 teams go. So now we know all 3 of these teams are going to the North America Championship. But what we don't know is who's going as the Greater New York Region Champion. Okay, because notice we have multiple pending runs on here. So the Columbia 0 team, they have pending runs on problems E and J. Let's take a look at the one for problem E. That's a yes. Hi. So now moving back down, the Cornell Alpha team has a pending run on problem E. Let's see what happens here. They're currently in 3rd place and having earned at least a bronze medal. Let's take a look at this submission. It's a Okay, so here we go. We're back to Columbia 0 again. They still have pending submissions on problem J, and the top 3 teams now have all signed, succeeded to solve 9 problems. So let's take a look at this one. Okay. Oh. Okay. So they are oh wait. Wait a second, huh? Okay, yeah. Pay no attention to what it says on the screen. They Columbia 0 team finishes in 3rd place and have earned the bronze medal, the most problem solved. The C++ Solution Award, most solved problems in C++, and copies of Yarn. Not just copies of Bjorn Strostrup's book, signed copies of
Okay. 1, 2, 3. Perfect. Okay.
All right, so, well, given that we've now run out of pending runs, that means the Cornell Alpha team solving 9 problems is in fact the silver medals team. Come on down. Our silver medalist team is not even here. Okay, I think we can. We give the medals to JetBrains. Right. Okay, well, one more color medal we're gonna say. Yeah, right, yeah. In first place, earning a pink medal, the Princeton team solving 9 problems in the minimum amount of time. Come on down, they are the. Oh, and the presentation of the Greater New York Regional Contest Trophy.
We go, smile, big smile. One more. All right, got it. All right.
All right. Okay, and I just want to say thank you very much to all of the competing teams. Congratulations. Everyone did marvelously. This is a great regional, and I've been to a lot of them. I'm going to turn it back over to the regional contest director, Joe Terlizzi.
Thank you. Hopefully, I hope everyone had a good time and see you next year.
Okay. Thank you all. Thank you.
Yeah.